Okay, it's 9, so we're gonna start. Good morning, everyone. Welcome to PyCon and to getting started with Kubernetes and container orchestration. You will find the slides that I will present this morning at this URL here, pycon2019.container.training. You will also find that URL on the little cards that we've put on your tables. So I'm Jérôme, and I'm helped today by AJ, who is on the back of the room over there. So we will run this until about 12:20. There will be a coffee break. It's more likely to be around like 10:15. I'm going to give a heavy responsibility to the people in the first row. If you see that at 10:15 I'm still obliviously going through slides, please throw something at me so that we can make a short break, have coffee, etc. Feel free to interrupt if you have questions at any time. And between each chapter, we've put full screen pictures of containers to remind us, oh, we're about to start a new chapter and we should take a deep breath and let people ask questions. In case you feel shy about raising your hand and asking questions, we've also thought about setting up a chat room using Gitter. There will be the link to that chat room in just a few slides, and you will be able to ask questions here as well live. And of course, I won't be able to simultaneously show slides and make demos and watch a chat room, but AJ on the back is going to monitor that chat room for your questions during the entire workshop. So the content that I'll present this morning was initially written for in-person training like this, but it can also be used or reused for self-paced training. The materials are going to remain online, maybe not forever, but at least for a really long time. So you are welcome to use and reuse them later. You can even look at the other materials that we deliver. There are also like 1 day, 2 day, 4 days workshops and training materials. So all the content is stored in a public GitHub repo. That repo has these slides, but also the code for the demo app that we will use this morning, as well as a bunch of scripts and other tools that can be useful to deliver content or follow this workshop. The source of the slides is in Markdown, and if you go at any slide to the bottom edge of the screen, you will see this black bar showing up, and if you click on it, it will take you to GitHub to the source of these slides, which will show up in just a hot second once the Wi-Fi gives me access to said material. Here we go. So the slides source are in Markdown, and the idea is to version them, keep track of changes, allow for easy pull requests, etc., etc. You will see, okay, so normally in the top left corner here, there should be a little magnifying glass. I don't know why it's not showing up, maybe, oh, there we go. It was just a small network glitch. You will see that these slides have 2 layers. There is the first layer that we are going to cover extensively today, and there is a second layer, which is indicated by these slides with the little magnifying glass. These slides have extra content that I will skip today, but that I wanted to have in the slides so that if you just like check on them later, or if we are covering a chapter about concepts that you already know, they will provide extra information and extra depth. But don't panic if you see me just like skip slides with that little symbol. It's normal, it's expected, because I don't expect otherwise that we would cover 300 slides in just half a day. So this is the outline for today. I will quickly cover the pre-requirements. Then we will run a demo app built around a microservices architecture on a single machine using Docker Compose. And then we will want to run that app on a Kubernetes cluster. So I will present Kubernetes concepts, including the emphasis on the declarative model of Kubernetes and reconciliation loops. I will quickly explain how networking works, and then once we're equipped with the theory, we will jump into the practice. We will do some things with kubectl, run a few containers on a Kubernetes cluster, see how to interconnect containers together. Then we will run the demo app on the Kubernetes cluster, and we will see 2 different ways to scale services. using deployments and replica sets, and then using daemon sets. This will give us an opportunity to see how to write YAML descriptions for Kubernetes resources. Then we will wrap up with labels and selectors, which are a pretty useful concept in Kubernetes, and a quick demo of rolling updates. And then I will give you a few kind of extra links and next steps, like what to do next after what we will have seen. And these are the famous full-screen container pictures I was mentioning earlier. So do you have any question about this? Can everybody hear me okay? Can everybody see the slides okay? All right. So pre-requirements. The pre-requirements are fairly minimal in the sense that I wanted anyone who wants to learn about containers and Kubernetes to be able to attend. So you just need to be comfortable with the Unix command line, because we're going to SSH into remote servers to do some things there. You need to be able to clone a repo, navigate directories, edit files with VI or your favorite command line editor, and maybe we will go as far as setting up our own variables and doing a few shell loops, but that's pretty much it. You need a little bit of container knowledge, but a very small, like bare minimum. If you know how to build a container image and how to run it, that's perfect. That's all you will need to know. It could be with Docker, it could be with another container platform, that's fine. There is some theory about education telling that we all have different ways to memorize things. Some people are able to just sit here and listen, and then they understand and they can do things. Some of us need to see someone do things, and then they can repeat that. Some people need to do things themselves, and then muscle memory kicks in. And some people need to explain to others, and the act of explaining to others helps them to actually remember. I'm more in the last category. But to help everyone to be able to understand and memorize what we're going to do this morning, each chapter I'm going to explain concepts, then run some demos, and then invite you to reproduce the demos in your own environment if you want to. You don't have to. Like for some people, running commands and listening, etc., can be a distraction. But if you're the kind of person who likes to do things, who likes like to follow how-tos and things like that, everybody will be given a private environment, a Kubernetes cluster, to run all the demos and labs. So precisely, like these demos and labs are going to be identified by these gray rectangles like this. And they will show the labs and exercises. So the first thing that I invite you to do is to open the slides. So if you haven't done so already, so that's PyCon 2019.container.training. That way you will have the slides. So if you are either very much on the back of the room and you can't see them really well, or if I'm jumping to the terminal to do some demos and you are wondering what was on the slide, etc., you will be able to always have the slides handy. You can see the slide number in the top right corner, and pro tip, if you type a slide number, it will jump to that slide number. Like if I type 42, enter, it takes me to slide 42, and then I can go back to wherever I was. The other thing I invite you to do is, once you have opened the slides and jump to slide 14, is to join the chat room by clicking on that link over there, the Gitter link. So this is going to open Gitter. And Gitter is, if you're not familiar with it, it's a little bit like Slack or IRC. It's pretty much like low-key, no frills, no super fancy features, but it's super easy to join the chat room. If you have a GitHub or GitLab or Twitter account, it should be just one click and you're in. So we pick that for simplicity. Again, you don't have to join the chat room, but it can be super useful if you have questions, comments, etc., etc. So I was mentioning that everybody would get a private Kubernetes cluster. So everybody gets a cluster indeed. And that's going to be with these little cards that should be on your tables. Just making sure everybody got one of these. If you can't find that little card, please raise your hand and we will magically get one to you. No, everybody has one? Awesome. So these are VMs that were deployed just this morning and set up with Kubernetes. Each of you gets 4 VMs pre-set up as a Kubernetes cluster. Unfortunately, since VMs cost money because cloud providers are trying to make profit these days, I will not be able to leave them online for a very long time after the workshop, but they will be online for today. So why are we not just running containers and Kubernetes locally? Because not all of us have machines that would be able to do that. Sometimes we don't have like the virtualization extensions enabled, or we might have some really restrictive IT policies in place preventing us from installing all that. And furthermore, most of the installation options to install Kubernetes locally will give you a one-node cluster. And for some labs and some demos, we want an actual cluster with multiple nodes. So to completely sidestep the issues, we're going to SSH into remote VMs. Oh, and one last thing, if it's like 70 people, all of us pulling images and building things at the same time over conference Wi-Fi, that's not going to be a pleasant experience. So instead, let's SSH into remote machines, because on the remote machines, the bandwidth is infinite, or almost. If you don't have an SSH client, because for instance, if you're running on Windows, on older versions of Windows, I've put some links in the slides here where you can get like PuTTY or something like that that will give you a way to connect into these remote machines. So the first thing that we're going to do is connect into the lab environment to make sure that everything works fine. And so in my terminal here, I'm going to do SSH docker at. Here I'm going to put the IP address of node 1. Of course, that's my node 1, not yours. Please put the IP address of your node, not mine, otherwise we're going to step on each other's feet. And once I'm logged in, I will just do one command to make sure that my cluster is fine. I'm going to do kubectl get nodes. And this is going to show me the list of nodes on my cluster. And I should see 4 nodes named node 1, 2, 3, 4. They should all be ready. And if by any chance you can't log into your environment, or when you do that command it shows something else, please raise your hand or let us know so that we can address that now and to make sure that you have a working environment for the labs. Everybody managed to log into their environment? Anybody had problems? No? Okay. If you are redoing parts of that later and you would like an environment, you can use something called Play with Kubernetes or Katacoda, for instance, that will give you a cluster in the browser. Obviously, the cluster won't be running in the browser. It will be somewhere on some cloud instances, but you will get a terminal in the browser letting you connect to a remote cluster. The only downside of these environments is that they are short-lived. For instance, Play with Kubernetes, the environments are destroyed after 4 hours of use. We will do almost everything with node 1. We won't really need to SSH into the other nodes. Node 1 will be our control plane. It will be our bastion host, our control center, if you will. Once in a while, I'm going to say, hey, let's open a new terminal and do this and that, because, for instance, we will want to see logs with tail-f or something similar and run some command and see the impact of that command in the logs. You can do either like have multiple windows and multiple SSH sessions to the servers, or in my case, I'm going to use tmux, which is a terminal multiplexer like screen. Just because as a presenter it's an easier option, but pick whatever you're the most comfortable with. It could be like multiple windows, it could be screen, it could be Tmux, everything is fine. Do you have questions on the environment? Yes? Oh, so if you get an error message, like if you do kubectl get nodes and you see like a connection to localhost 8080 was refused, this is probably because you're not on node 1, but on node 2, 3, or 4. Yeah. Is that the case? Yes, the kubectl command is only going to work on node 1 because the configuration file that kubectl requires is only deployed on node 1. Yeah. Okay, so without further ado, we're going to see the demo app that we're going to use for the whole morning. So for starters, we're going to run that demo app with Compose just to bring it up, see how it works, and then we're going to tear it down and see how to deploy it on Kubernetes. This demo app is on the same repo that has the slides and scripts and everything else. And so I'm going to clone that repo. Git clone, https, github.com, jpetazzo, that's me, /container.training. And in that repo, I have a bunch of things. For instance, the slides directory, as you might guess, has the slides. But the demo app that we want to run is called Dockercoins, and it's in the subdirectory Dockercoins. When I go to that subdirectory, I see a Docker Compose YAML file. Without diving into too much details, when you see a Docker Compose YAML file, it means we can run this with Compose. It's a little bit like when you see a make file, you know you can run make. When you see requirements.txt or setup.py, you know you can use pip or Python setup.py to install dependencies. If you see a gem file, if you also do Ruby, you know you can use bundler to install that. You can also see like package.json for Node.js applications or POM.xml for Java deployed with Maven, etc., etc. So when I see docker compose.yaml, I know I can just do docker compose up. And this is going to read that YAML file, analyze it, and build and run the application. While it's building, I'm going to have a quick look at the compose YAML file. And in that compose YAML file, I see that I have a bunch of services, each of them corresponding to one container. And for each service, I can either have an image statement, which means just get an existing image from a container registry. So in that case, I have a Redis service, and I say just use image Redis. And then I have a bunch of services for which I have a build statement. And there is one free space over there. And if you have a free space next to you, can you raise your hand as well? Okay, there are a few more spaces over there as well. I counted 69 seats, and I think there were 67 people registered, so there should be one seat for everyone. Okay, so when you see a build statement, that means that we're going to build a container image using a Dockerfile contained in the directory indicated by the build statement. So for instance, here I have RNG, build RNG. That means there is an RNG directory, and in that RNG directory, there is a Dockerfile and a little rng.py file. Okay, while I was explaining all that, the app should now be running, and Compose has created all the containers for the application and is now showing me the logs for the application. If I do a little freeze, like just for a second, we can see that we have what looks like HTTP logs. I have some get on RNG and some post on hasher. And once in a while, I have worker saying something about X units of work done, updating hash counter. So what exactly is this application? It's a Docker coin miner. Fortunately for the environment, but unfortunately for my retirement plans, Docker coins is not an actual cryptocurrency. You can't buy anything with it. What Docker coins is doing is that it's an infinite loop where we are generating a little bit of random data, hashing that random data, and incrementing a counter. And we do that again and again and again. So in Python, we use like random.random, and then we use like SHA-256 to compute that hash, and then we increment a counter. But since that would not be a very interesting example, we are kind of spicing things up a little bit by having the random number generation part being in a web service. So that's the RNG service, random number generator. And so when we need to generate random data, we do a get on the RNG service. And then when we want to hash the data, instead of just calling like a built-in crypto package, we post the data to the hasher service. And when we need to increment the counter, instead of doing like counter plus equal 1, we store the counter in Redis and we increment that counter in Redis. And finally, we have a nice little web UI that will allow us to see the speed at which the whole thing is working. So if you like diagrams, that's a diagram showing how that works. So worker, doing get request to RNG, posting to hasher, incrementing things in Redis, and then the web UI. Speaking of, so how does these things connect together? So we don't need to hard code IP addresses or service names in the code. We just put the name of the service itself. So when I want to connect to Redis, I put the name Redis. When I want to make a web request to RNG, I do a request to http://RNG, and so on and so on. So it's kind of one step beyond 12 factors because I don't even need to change environment variables when I deploy my application from one environment to another. How does that work? The container engine is going to expose a dynamic DNS service where the name Redis will correspond to the IP address of the Redis container, the name RNG corresponds to the IP address of the RNG container, and so on and so forth. And once we will deploy on a cluster, we will have a global DNS service that will fill exactly the same role so that the code keeps working the same way. Okay. So logs. I mentioned the web UI, so we're going to have a look at that. The web UI is on port 8000. We know that port number either from the Docker Compose YAML file. We see here ports 8000:80. And I'm going to connect to that port 8000. So I'm going to put the IP address of node 1. And then port 8000, and I should get a magnificent web interface with a blue graph here showing me how fast my Dockercoin app is running. So our goal will be to run that on Kubernetes and then find ways to scale that up so that this counter goes higher than just 4. Okay. So before moving on, we're going to shut down the app and clean up what we've done before we move on to Kubernetes. So I'm going to stop the app by hitting Control-C. Okay. Let's see. There we go. Okay, I did hit Control-C twice in a row, a little bit too fast, so all my containers did exit very quickly. But if you hit just Control-C once, what you will see is that 2 containers stop immediately, and the 3 others take a little bit longer. I'm going to try to show that. Let me restart the application. I'm going to give it 10 seconds to start. Oh, that's great. That's good. I can introduce that as well. The worker is running in a kind of crash loop mode. If there is any problem, any exception, any problem whatsoever, it just displays the exception and then it waits 10 seconds and start over. So that's why we saw this trace back in the beginning, because it tried to connect to the other services. The other services were not up yet, so it crashed, but when it tried again 10 seconds later, everything was up and running and everything worked fine. So I hit Control C. I see, okay, that's a glitch. I probably hit Control C twice again. Please ignore that, but 2 services are handling the term signal properly. That should be Hasher and Redis, and so they exit right away. And the 3 other services are ignoring the signal, so they will keep running, and 10 seconds later, the container engine is going to kill them. This will become more relevant later when we will do rolling updates. Why? Because if I just have a couple of services, and I'm just like, for now, the only downside of this is that when I stop my app, I have to wait 10 seconds for the app to be down, so no big deal. Now imagine that I'm doing a rolling update where I have 100 containers and I want to upgrade these containers, and I want to do that smoothly, so I don't want to shut down everything and restart everything. I want to take each container one by one, shut down, bring the new version up. Once the new version is up, I shut down the next one, bring up the new version, etc., etc., etc. And now imagine that this timeout, instead of being 10 seconds, it's 1 minute. So now, instead of just waiting 10 seconds for my app to quit, I'm going to wait 1 minute for each container to be upgraded. If I have 100 containers, that means waiting 100 minutes, which means 1.5 hours just for an upgrade, which would take just a couple of minutes if I had handled signals properly. Right. So, and the last thing we will do before moving on is Docker compose down. That's the opposite action of Docker compose up. So it's going to shut down things, but also remove the containers and clean up all the resources that were allocated for this demo app. Okay, we're back to a pristine condition, and we can move to Kubernetes. Do you have questions on that app and on what we've done so far? Yes? What's the difference between Control-C and down? When I do Control-C, I'm just sending like Control-C is the equivalent of Docker compose stop. And then there is Docker compose kill, which goes like one step further and forcibly shut down the container. And then I have Docker compose down, which is going to remove the container. So instead of just being stopped, they are going to be deleted. And resources like the network that was created for the application is going to be removed as well. And if I had volumes, databases, and things like that, I would even be able to do Docker compose down -v to say, and also remove the volumes, which is not done by default because we don't want people to lose their databases with a little mistake like that. Okay. So, I'm going to present the concepts of Kubernetes, just like a high level, what we need to know before we can use it, and then we are going to roll up our sleeves and actually use Kubernetes clusters. So if we look at a kind of a Wikipedia-style definition of Kubernetes, we learned that it's a container management system, which doesn't really teach us anything useful. So instead of going to give you a more of a functional definition, you know, like in Python, we like to do a lot of duck typing. So we define what a thing can do so that we know what it is. So in Kubernetes, that's a list of the things I can do. This slide is going to show the things we can do and will do today. And on the next slide, I have some more advanced concepts. So let's pretend for this example that I have an e-commerce website, and I decided to break that down into multiple tiers. So I have a web front ends, and then I have an API server, and then I have my database somewhere. So I want to deploy multiple containers running my API backend, and I want to set up an internal load balancer for these API containers. Then I want to deploy a bunch of containers for the web front end, and I want to add a load balancer, but a public one this time. And then, since I'm doing e-commerce and it's either Black Friday or Christmas or whatever, I need much more containers to deal with the spike of traffic. So I want to be able really easily to scale up and add more containers, add more nodes to the cluster, add more containers. And then, of course, since my code was written by humans, and humans make mistakes sometimes, I notice I have bugs and I need to roll out a new version. But of course, it happens right in the middle of peak traffic, and I don't want to put the whole website down while I do a maintenance. So I would like to do a smooth rolling update. So upgrade to a new version, but like when I was, just like I was describing earlier, one container at a time without stopping everything else. So that's the kind of things that we're going to do today. More advanced features include auto-scaling. So instead of me manually eyeballing traffic and metrics, I will want Kubernetes to decide by itself how much containers there should be so that I can attain my SLOs. I can do blue, green, and canary deployments, which are like safer ways of deploying things. I can not only run web services and workers, but also batch jobs. I can also overcommit my cluster and use priorities so that if I have too much things running, it's going to be able to evict low priority workloads, so to keep the main production things running. I can run not only web services and like stateless services, but also stateful services like databases, message queues, etc., and much, much more. Now, so that was a kind of functional definition, what we can do with it. Now, next, I want to show a little architecture diagram. So you probably have heard that Kubernetes was complicated and there were like many concepts and objects. Don't worry, as you can see on this diagram, it's pretty simple. Okay, no, that one is just to check if you are awake. Thanks for laughing at my joke. This is the actual diagram, and I'm going to break that down for you. On the left-hand side here, the dark blue rectangle, that's the control plane. That's the brains of the cluster. Each time we want to interact with Kubernetes, that's going to be through that. We're going to talk to this control plane, and then it's going to figure it out with the rest of the cluster. Then we have the nodes, which will run our actual containers. So the actual containers are the little colored rectangles here. They run on a container runtime, which often will be Docker, but could be anything else, because now there are many other options. That container runtime is going to be running on an operating system, which often will be Linux, but now you can also run Kubernetes on Windows, and that operating system is going to run on some infrastructure, which means servers, physical machines, virtual machines, anything goes. On each node, we have a couple of components that will kind of connect that node to the cluster, kubelet and kubeproxy. Kubelet is a little agent that sits here and connects to the control plane to say, hello, I'm node number 44. Do you have any containers I should be running? The control plane will say, oh, welcome, node 44. Please run this and this and this container. And then kubelet will start these containers and monitor them and continuously update the control plane with the status of these containers. So when you read about kubelet, that's the little agent that sits on each node and keeps the node in the cluster. There is also kubeproxy, which is one part of the network story, and I will tell more about that in a bit. The scary diagram was an actual Kubernetes diagram, but using like there is a SAN in the middle, accessed with Linux LVM over multipath and a few other features. So it's an actual Kubernetes diagram, but a fairly complex one indeed. Okay, so nodes. Now the control plane. In the control plane, we have a handful of components. The API server is a notable one because everything will go through the API server. When we will control the cluster, we will talk to the API server. Kubelet connects to the API server. The other components of the control plane also connect through the API server. So it's a little bit like a big connection point, a hub, if you will, for everything else. Then we have a few other components in the control plane. We have etcd, which is the database storing all the important stuff of the cluster. And then we have controller manager and scheduler. what we should retain is that etcd is the only stateful thing in that control plane. It's the only thing storing information. The other components are stateless, meaning that I could destroy them and recreate them and everything would be fine. However, if I lose etcd, I'm toast. As for the other components, we can ignore their exact role for now. It's fine. Okay. When we interact with the cluster, we do that through the Kubernetes API, which is a mostly REST API, and it allows us to, do the classic CRUD, create, read, update, delete on resources. The Kubernetes resources are things like nodes, like the machines of the cluster, pods, which are groups of containers, more on that in just a minute, services, which are a network construct, we'll also talk more about this, and many, many, many others. So in a way, the Kubernetes API server acts as an intermediary between us and a bunch of objects stored, persisted in etcd and with strong typing. So a node is fairly easy to understand. It's just a machine, part of the cluster. Now a pod is a little bit trickier. A pod is a group of containers that work together and are always scheduled running on the same node. You can't have a pod straddling across multiple nodes. And when we scale things up, we scale pods, we don't scale inside pods. So what I mean by that is, look at this example where I have Nginx and a logger. So the assumption here is that there is Nginx serving web traffic, writing log files, and next to it there is a logger that gets these log files and sends them to maybe Splunk or Stackdriver or CloudWatch or Elasticsearch or whatever I have to manage my logs. If I need to scale up, I'm not going to add more Nginx inside that pod. I'm going to add more pods like this. Because if I put multiple Nginx containers inside that pod, since the pod is always on one single node, I'm just ending up with maybe 5 Nginx on the same machine, and usually that doesn't really help me. So what I want is multiple pods with the same purpose. All the content, yeah?
Sorry, so it's always the node to pod relationship is always 1-to-1?
Is the node to pod relationship 1-to-1? No, the one node can have as many pods as we want. A pod is it's a little collection of processes, of containers that work together. So for instance, if I'm using a WSGI app, but I also want to have maybe Apache or Nginx to serve static content, I might decide to have in a single pod, let's say Nginx and UWSGI, and together in the same pod. And then when I scale up, I end up with multiple pods like that. But on a given machine, I might have this Nginx UWSGI pod, and also a PostgreSQL pod, and also a pod for a completely different application, etc., etc., etc. All the containers in a given pod have the same IP address. So if you've done some networking, at first this might seem extremely upsetting, because usually when we have multiple things with the same IP address, we get IP address conflict, and one thing works, the other doesn't, and sometimes it randomly flips from one to the other. So here you can imagine, if it helps, that each pod is a little bit like a micro virtual machine in which we have multiple things running. So the pod has an IP address, and everything in that pod has the same IP address, and everything in that pod can communicate over localhost, for instance. Right.
So these called sidecar also.
So what about sidecars? Yeah, you will often see the sidecars in Kubernetes. A sidecar is a container in a pod that provides some extra feature, some extra little thing. For instance, here we would probably call that logger a logger sidecar or logging sidecar. When we use service meshes, without diving into too much details, but we end up with a sidecar whose purpose is to intercept the network connections that your code is making and route them to the right service, add some instrumentation, etc., etc. So we could have sidecars for pretty much anything. It just means a container that we add into a pod to add some extra features in that pod. Right. Other questions on these concepts? Yes? What happens if the control plane dies? When the control plane dies, everything else keeps running. So all my containers, my pods, my applications, everything keeps running and everything is fine. And everything is designed to kind of keep trying and reconnecting. So for instance, if I disconnect or reboot my control plane, the kubelets on each node are just they're going to notice, of course, but they're not going to terminate containers or anything. They're just going to try again and try again and try again. And once the connection is up again, they're going to resynchronize. So they're going to say, I'm node 44. I'm currently running these containers. What should I be doing now? And if my etcd hasn't been corrupted or wiped out or etc., the state on the control plane is still the same. So the resynchronization is fine. Now, on the other hand, if we wipe out etcd, for instance, and the control plane comes back, when the node reconnects, it's going to be extremely confused, and undefined things, bad things might happen. It will depend on the details, but yeah. So that's, yeah. Of course, there can be some specific things that will rely on the control plane. Let me give you an example. Let's say I have a bunch of workers that are pulling messages from a Kafka queue. And I want to dynamically add workers if the Kafka queue grows too big. Like I said, if I have more than 1,000 messages in the Kafka queue, I want to add workers. And I add workers by talking to the control plane. So of course, in that case, if the control plane is down, I'm not able to add workers until it's back up. Does it work as a cluster? So is the question like, how do we ensure the availability of the control plane? Right, so if we look at this diagram over there, the etcd itself is designed to be highly available in the sense that we can set it up as a cluster with typically 3 or 5 nodes. And when we say highly available, it means that it's not like, for instance, a replicated SQL database where I have a primary and a replica, and when the primary goes down, I still have to do some operations to switch traffic to the replica, which can be almost automated sometimes with something like PG Bouncer or MySQL Proxy, etc., etc. In the case of etcd, high availability was built in, like designed from the very beginning. So I have like my 3 or 5 etcd nodes, and I can issue requests versus any of them. And if any node goes down, everything else keeps working like without a single interruption. And if I'm making a request on a node, and at that very moment the node blows up, I will get an error, and I know I just need to repeat my request on another node, and it will be fine. So that's how it's designed for high availability. The other components are stateless and are also designed to be replicated. So the API server can be scaled without anything special. And then I can talk to any API server. And since everything goes to etcd behind the API server, it will be fine. And as for the 2 other components, controller manager and scheduler, they are using an active-passive replication mode where one of them is going to acquire a lease on the API server and say, hey, I'm the active scheduler now. And the other schedulers are going to stand by and until that lease expires. And then they're like, oh, the lease expired, which means the active went down, offline, so I'm going to take over. So that's how we achieve high availability. Yeah? Who's responsible for making sure that etcd stays available, you mean? Like if I'm running my own cluster, like, there are a couple of ways I could answer that question. Like if we're talking about, hey, I'm a developer and I'm using a Kubernetes cluster, whose responsibility is it to maintain all that stuff? Then the answer is not us. Generally, we will either use a managed Kubernetes, or we will have folks responsible for setting that up on our machines. So as a user of Kubernetes, like deploying my apps on Kubernetes, it's great that I know what's behind the scenes, but I won't have to operate and maintain and etc. etcd to deploy my applications. Right. More questions? No? Okay. So, Kubernetes puts emphasis on being declarative. So this means that I'm giving an example with tea, for instance, where the declarative mode is when I say, I would like some tea, and then some things happen, and boom, tea happens. The imperative mode is I give a recipe, which is like step 1, boil water, step 2, add tea leaves, step 3, power the tea in a cup. So at first, we could think that the declarative mode is simpler, because I just say I want some tea, but it requires to know how to brew tea. And then I need to explicit, like, okay, so a cup of tea is an infusion of tea leaves that you put in a cup. What's an infusion? Well, an infusion is when you put the thing that you want to infuse, like the tea leaves, in hot water for a moment. How do you obtain hot water? By warming up cold water, etc., etc. So now, once we explicit that, the imperative version is way simpler, because it's just like step 1, step 2, step 3, done. However, if we have an interruption, if like in the middle of brewing tea, I'm getting a phone call, or somebody asks me to do something else, with the imperative version, I have to start over, because maybe I was interrupted for 10 seconds and it's fine. Maybe I was interrupted for 1 hour, and if my water was boiling, now it's completely evaporated, or maybe it's cold again, or maybe I had put the water on the tea leaves, and now after 1 hour my tea is completely undrinkable, etc., etc. So my only option is to start over. However, with a declarative system, if I'm smart enough, if I realize, like when walking into the kitchen, okay, I already have hot water, so I can skip that step. Or, okay, we already have tea leaves in some hot water, so I don't need to do that again. So the declarative system will be able to recover from problems more easily. But it implies that I'm able to observe the system. I need to be able to figure out what I have and to compute a diff between my recipe, my instructions, and what I already have. So Kubernetes is a declarative system, which means in concrete terms that I cannot tell Kubernetes, run that container. What I can do is write a spec that says, I would like that container to be running. Then I send the spec to the API server, and the API server then works on it and makes that thing happen. So when I do an API request to Kubernetes, what I'm really doing is storing something in etcd, and then I will have a bunch of control loops, the controller manager I was mentioning earlier, who are going to wake up and work on these specs. So that's how it works. I have a little diagram I would like to show. It's not in the slide themselves because I'm still working on that, but boom. Will that work? Yes, wonderful. So this is like this comes from the Learn Kubernetes website, but I've slightly adapted that to add some extra steps. So this is like the state of my cluster at rest, no pun intended. And the first thing I do is I connect to the cluster and I say, hey, I would like to create a bunch of pods running my application. So by doing that, I'm going to store, for instance, a replica set. We're going to talk about that in a while, but I'm storing a replica set specification in etcd. And then I can go away and I'm done. Like the API tells me I got it, which doesn't mean that my containers are running, but it means I got it, now things are going to happen in the background. Then there is a controller manager that is observing resources and it's like, oh, there is a new replica set, we need to do something about that. It's like, what is this replica set? Oh, you want 3 pods like this? Fine, I'm going to create 3 pods in the storage backend. These pods will be in pending state, which means that we haven't decided yet where they should run. So at this point, the scheduler, which I also like to call the Grandmaster of Tetris, is going to wake up and see, okay, we have pending pods, we need to decide where to run them. In that case, we have only 1 node, so it's an extremely difficult decision. But after assigning the pods to the node, they are now scheduled, and then the scheduler goes back to sleep. And then after that, the sync loop between the control plane and kubelet kicks in and says, hey, node number 44, because I like node 44, you should be running these pods. So kubelet is going to pull the image for that container and run these pods. And at this point, everything is up and running, and I'm done. So that's how it works behind the scenes. Questions? Yeah?
So once it's running, it goes out of scheduled state and into a running state?
Oh, yes. Once it's running, we will see the life cycle of the pod going from like pending, then it will go to like container creating, which really means it's pulling the image and creating the network, etc. And then it will go to running, and then at some either it stays running forever, or it will go to completed or failed state, depending on the spec and how it exits. Yeah. And if you like details, once a pod is completed or failed, it can't come back up. So it's like a one-way thing. It's not a cycle. So if the pod dies and we need a new pod, then we get a new pod. We don't resurrect that pod. Yeah.
So which thing, okay.
Yeah. Yeah.
So which thing comes first, readiness or readiness and liveness?
Oh, which one comes first between readiness and liveness? So readiness and liveness are 2 health checks in Kubernetes. I'm going to give you a really short answer because it's a little bit more advanced, but there are 2 health checks that we can run on containers within a pod, liveness and readiness. And to remember which is which, I think about the fact that for liveness, once something is dead, you can't bring it back to life. So there is no undead pods or whatever. So the liveness check, once it fails, that means, okay, that container is like broken beyond repair, and we need to restart a new thing. However, the readiness means like, are you ready or not? And if you're not ready, then eventually you might become ready again. So the readiness check can go like ready, not ready, ready, not ready. So the liveness probe is going to be used to assess, okay, that container has a problem, we need to restart it, while the readiness check will be used to say, okay, that container can't handle traffic yet, so we're going to remove it from the load balancer rotation, for instance. Yeah.
Can you explain again what the replica set?
Oh, what's a replica set? I'm going to talk more about the replica set in just a moment, but for now we can just say, okay, it's a thing to create a bunch of pods, but I will give more details shortly. Yeah. Right. So, one more thing, the network model. So this is just going to, I'm going to be relatively quick on this. The short version is that on Kubernetes, we have one big flat network. So we have nodes, so the machines and the pods, the containers, everything is on one big flat network, and everything can ping everything directly. We don't need to map ports. We don't need to do, it's pretty simple. And there is no NAT. And one little implementation detail is that the IP addresses of the pods are assigned by the network layer. I'm not going to say I want this IP address or this IP address. This is going to be assigned by the network implementation. And that's all there is in the spec. And then everything else, all the little details can be implementation dependent. So it doesn't mandate to use any particular protocol or encapsulation or et cetera, which means that on the upside, that's pretty simple to reason with. I don't have to think about, again, like mapping ports. I don't have to think about introducing a new protocol like VXLAN or et cetera in my network. I don't need to worry about porting IP addresses from one node to another. The network layer can decide all these details by itself. So that's great. So that means that we can have many implementations of the network on Kubernetes, which is both great and not so great when you get started, because when you set up your cluster, you reach the point in documentation that says, now pick one of these 15 network implementations before you move on. You're like, thanks. So it's great because for virtually every situation, cloud, on-prem, IoT, et cetera, there will be something to help us. But it means that when to pick the right one, it will incur a bunch of research to make sure we're making the right choice, basically. It also means that from a security standpoint, since everything is one big network, we have to think about that, and we have to add another layer of isolation. Like if on the same cluster, if I deploy multiple applications, by default, these applications will be able to communicate together. And if I want to isolate them, I will have to learn about network policies and implement that. Okay. In practice, on the clusters that we're going to use today, we've used a network implementation called Weave. Weave is the kind of all-wheels drive network layer of Kubernetes because it works everywhere on all terrains, cloud, on-prem, etc. So for that, it's pretty convenient. It's super easy to set up. I'm not saying that it's the best one for every situation, but in doubt when getting started, it's a pretty safe bet. Okay, I have some extra details here if you're the kind of person who really wants to know what's under the hood for the network, but I'm setting that aside. All right, now we know what we need to know to get started with networking on Kubernetes. Do you have questions on that part? Yes? Is it possible to have like multiple environments on the same cluster that are isolated? Yes, there are many ways to do that, but the easiest way is going to be using something called namespaces. And namespaces are a little bit like folders in which we can put pods and services and other things. And then when we define policies, whether it's network policies for firewalling or whether it's airbag to define access control rights, we can do that on a namespace level. So for instance, if I have, let's say, 2 copies of my Docker Coins app, and so in one copy I have a bunch of things that need to talk together, then I have the other copy with, again, same bunch of things that need to talk together, but I don't want like traffic to go between them. I could deploy everything in one namespace and then write a bunch of network policies to say this is allowed, this is allowed, this is allowed, etc., etc. Or I could put each of them in one namespace and then have a kind of, let's call that a blanket statement saying all these things in that namespace can communicate together, but not the outside. So that would be a relatively easy way to do that, easier at least than defining like one by one all the network flows that we want to allow. Same thing for access control. Let's say I want to give to someone access to the objects of that application. I could do that one by one, like, okay, Alice can access to this pod and this pod and this pod and this load balancer and this and that. Or I could say Alice can access all the objects in that namespace. So when I want to have multiple applications, typically, like most often times, I will want to use namespaces because it's so much easier. Other questions? Right, time to get started with kubectl. So kubectl is the Kubernetes CLI. It's just a glorified version of curl, if you will, because each time we do something with kubectl, it's going to craft an API request, send that to the Kubernetes API server, and display the result. So everything we do with kubectl, we could do with curl if we were slightly masochist. So kubectl is using a configuration file to know like where is the API server and what kind of credentials we should use. So that's kubeconfig. So for instance, if I look here in home/.kube/config, I will see that config file. And in that config file, among other things, I will see the address of the API server. And I'm going also to see a TLS certificate and key that are used to communicate with the API server. Right. One little thing. Since I'm French, as you probably noticed from my accent, in French, when we have like acronyms, we typically spell them out. So I'm almost always going to say kubectl, but other English speakers will often say kubectl, kubectl, kubecontrol, kubectl, or even other things. I will stick to kubectl, but no judgment whatsoever. The first command that we're going to use is going to be kubectl get, and kubectl get will list all the resources of a given type. So for instance, if I do kubectl get nodes, which we did like almost 1 hour ago when I said, hey, let's check everything works correctly, that means list all the nodes. And for each resource type, we have the plural form, the singular form, get node, and the short form for lazy people like me, which is kubectl get no. The point of having kubectl get node singular is because we can also give a node name behind that. So I can say kubectl get node node1, and then it's going to show me only node 1, for instance. The point of the short form kubectl get no is to save a few keystrokes, and also if we had a name called satisfaction, we could do kubectl get no satisfaction. But anyway. We can also change the output format to get a little bit more information. So for instance, I can do kubectl get nodes -o wide. So wide is going to add a bit of information. So just to contrast, this is adding a bunch of columns showing me the internal IP address, which OS we're running, the kernel version, container runtime, and this will work with all resource types. When I will show pods or this or that or whatever, each time I can use wide format to get some extra stuff. Okay. We have other output formats. For instance, I can do get nodes, let's use the singular form because it will make more sense. Get node node1 -o JSON. And that gives me JSON output with a lot of information about that node. And JSON is great for machines, but I'm a human, so I'm going to ask for YAML, which is slightly more readable, only slightly. And here you will see, like in the output, notice how we have API version, kind, and metadata. Every single API response from Kubernetes, like every single one of them is going to have these fields, always, always, always. So in that case, this is telling me, hey, this thing is a node. So I could go to the API specification. It would tell me, okay, if the type is a node, then it will have this and this and this and this field. It would tell me I have a spec and I have status, etc. And it would tell me about all the fields I can expect there. Now, for instance, if I do get nodes without indicating which one I want, the output is going to be still API version. I don't see a kind here, but if I look for it in the output, there it is. It says kind list. There is also a metadata. It doesn't carry anything useful, but I still have metadata. And then if I look into the API specification, it tells me the objects of kind list have a field called items. Indeed, I have items. And the value of items should be a list of things. And each thing, again, will have API version, kind, metadata, and a bunch of things. Okay. So the YAML can be useful because it's a little bit more readable than JSON. And JSON can be useful because you can parse it, of course, with code. But if you don't want to break out the interpreter or IPython to do some little things, you could use JQ, for instance, which I really, really like. And with, like, for instance, if I want to get some information about Node 1, I can do things like that, for instance. If you don't know about JQ, I recommend that you make a note to look on that a little bit later because it's awesome if you want to process some JSON from the shell. All right. Okay. So, yep, I told about the fact that we had plural form, singular form, short form. That's great. We can get some details. And I said, okay, so we have JSON, YAML, but we also have another form, which is kubectl describe. It's a different verb because it's going to kind of consolidate information coming from multiple places. But for instance, if I do kubectl describe node 1, it's going to show me a bunch of things coming from kubectl get, but also collate with other information. For instance, here, it's showing me the pods currently running on node 1. This is a little bit smaller on the screen, so I guess you can't really like see exactly what's here, but I'm going to tell it for you. This is telling me that on node 1, I have core DNS, I have etcd, kube API server, kube control manager, kube proxy, kube scheduler, withnet. So these names will remind you the names of the control plane that I gave earlier. This is showing me that on node 1, I have the control plane of my cluster running in pods. Okay. Right. Next object types, I have services. So services, services, or SVC for lazy people like me, services are an interesting network construct. We can think about them as either static IP addresses for pods, or also load balancers, or also things allowing you to reach something else. In the early versions of Kubernetes, services were called portals. And to be fair, I preferred that name way better because it represents more like what it really is. A service is a stable network endpoint. And what that really means is that when we have a pod running, as I said earlier, the IP address of the pod is assigned by the network implementation, which means that if my pod has a problem and another pod needs to be created to replace it, that other pod will almost certainly have a different IP address. So if I need to connect to that pod, I will need to update my IP addresses, and that sucks. So instead, I can use a service, which is going to give me a stable IP address, and then I can connect to that address, and that address will then redirect me or route me to the actual pod. So for instance, in that case, I see that I have a service called Kubernetes with a cluster IP of 1096.01. If you've done some networking, you can also think about that cluster IP like a service IP or virtual IP. And so this IP, like I can, hey, can I ping it? No, I can't ping it because implementation details. And because a service is a layer 4 construct. So if you studied like the 7 layers networking model, that maybe rings a bell. If you haven't, don't worry about it. What it really means is that the service, I have to specify the port of that service if I want to connect to it. Here in the output, we see that the Kubernetes service is on port 443. That means I have to connect to that specific port. So I know that 443 is HTTPS, so I'm going to hit that IP address with curl and HTTPS. And if I hit that service on any other port, it's just going to time out. Like my packets are going to dev null to the great void and never come back. But if I connect to port 443, then first I get a certificate warning, of course, because doing HTTPS on IP addresses like that doesn't work. But if I tell curl, okay, don't mind the certificate, I get something that looks like a Kubernetes API reply. You know, like there is a API version, kind, and metadata. It looks like an API response because it is an API response. That Kubernetes service, that's the Kubernetes API, and I can access it from within the cluster. This is giving me a kind of introspection, a kind of entry point into the API that I can hit if I need to. In that case, it's telling me failure. You are system anonymous because I did not provide any certificate or any token or any whatever. So the API could not find out who I was, so it thinks I'm anonymous. And by default, anonymous can't do anything on the Kubernetes API. Right. Okay. Next object type, pods. So I can do kubectl get pods, and this is going to list me my pods. And it's telling me no resources found, and that's slightly surprising because just a few minutes ago, we did a describe on node 1, and we saw a bunch of pods. So we know that this is a lie. We know there are pods and something is hiding them. The answer to that is namespaces, which I mentioned just 10 minutes ago to answer a question. We have namespaces that allow us to organize resources. And so namespaces are a resource like any other, which means I can do kubectl get namespaces. Or for lazy people like me, kubectl get ns. And then I see I have default kube node list, kube public, kube system. You might guess that by default, when we do kubectl get pods, we see the pods in the default namespace, and you would be right. And you might remember, if you did like squint your eyes a little bit when I was showing the kubectl describe on node 1, you might remember that here it showed kube system. So the pods of the control plane are running in the kube system namespace, and that's why when I do kubectl get pods, I'm not seeing them. If I want to see them anyway, I have a handful of options. One of them is to say, okay, show me all the namespaces. Get pods, all namespaces. And in that case, I get the list of all pods across all namespaces. Since Kubernetes 1.14, we can even abbreviate all namespaces in -A, and this feature just by itself justifies upgrading to Kubernetes 1.14. And I can also ask to scope to a specific namespace. So I can say -- namespace kube system, and then it's going to show me only what's in the kube system namespace. Okay, so we have pods. We see here the control plane pods. We see also a few interesting things, like for instance, I have 4 pods, kube proxy, yada yada, and 4 pods with net, yada yada. Like, why would I need multiple identical or seemingly identical pods? Because these pods are, okay, these pods are running like 1 per node. For instance, if I look at the 4 kube proxy here, and I switch to -O wide, so give me extra information, I get the IP addresses of the pods, and I get a node column that tells me that I have 1 on node 1, node 2, node 3, node 4. So 1 copy of kube proxy per node. Same thing if I look at weave here. Reminder, weave is the thing giving me the network connectivity between my nodes. And again, I have 1 copy of weave running on each node. Okay. So it looks like etcd is running on node 1. So if we do something bad with node 1, we might do something bad with etcd.
The mental model, I'm just trying to understand what responsibilities we might have about etcd, and then
What will be my responsibility with etcd?
all the
Right.
runtime you're dealing with, or like I was surprised to see etcd listed under node 1.
Sure. So there is a handful of slides that I skipped on, like in the extra details about like where should the control plane be running, and we have actually many options. The control plane, like if I want to give you, you know, the kind of dictionary style pedantic definition, the control plane is a bunch of processes that implement the Kubernetes API. But that control plane could be running anywhere. In that case, we are, I would say, partially self-hosted. So self-hosted meaning the control plane for Kubernetes runs on Kubernetes itself. And I say partially because it's little details. Like for instance, I can't update it using Kubernetes primitives and commands. But that control plane could be completely outside. For instance, if I deploy a Kubernetes cluster on Amazon EKS or Google GKE or Azure AKS or DigitalOcean or OVH or pretty much all the managed Kubernetes offerings of cloud and hosting providers out there, they are not going to run the control plane on my cluster. They are going to run the control plane somewhere. I don't get to know where. They don't tell me. Well, sometimes they tell you because they make like talks about it and etc. But for me, that's going to be an implementation detail because all I will be able to see is an API endpoint. I connect to that API endpoint, and for all practical purposes, all the commands I was running here would work exactly the same way, except all these processes like etcd, API server, controller manager, scheduler, they will all be running somewhere else. And so in that case, it's not my responsibility to maintain and back up and operate that control plane.
How often do we expect to need to care about the things that are running in the kube system namespace?
How often do we expect to care about what's running in the kube system namespace? Only if you are operating the Kubernetes cluster yourself. For many scenarios, I often do the joke that the easiest way to install Kubernetes is to get somebody else to do it for you. But it's also very true. Kubernetes is a pretty complex beast to operate. My goal this morning is to show you that using Kubernetes is going to be relatively straightforward. Once we've wrapped our head around the concepts, we'll be able to run apps on it. However, operating Kubernetes itself is a whole different story. It's a little bit the same difference between I can write a Python app and I can compile my own kernel. It's like I don't need to compile my own Linux kernel if I just want to run a Python app. So likewise, I don't need to be able to know how to deploy and upgrade and maintain Kubernetes to deploy apps on it. So most of us hopefully won't have to ever worry about how do I maintain that control plane, etc. And in some scenarios, for instance, if I work for the military or nation state or something like that and I can't use the cloud for regulation purposes, then I might have to learn how to operate my Kubernetes cluster, but most of the times I won't have to. I think so, yeah.
Is Weave the network implementation that dictates the IPs for each pod, or what is Weave?
What is Weave? So Weave here is the network implementation that we are using to provide what we call the pod network. So the connectivity between pods is going to allocate IP addresses to the pods and plumb them into some kind of network fabric so that all the pods can ping each other, so that the nodes can ping the pods and vice versa.
And you have to select this type of network implementation?
And we have to select a network implementation indeed. Weave is a kind of easy choice, but there are many others.
Is this part of Kubernetes?
Is this part of Kubernetes? Kind of. I mean, Weave doesn't come with Kubernetes. It's an external product, but the constructs that it uses, etc., are very well integrated with the rest of the ecosystem.
Is there like a default that
Is there a default network implementation? Not really. There is a kind of a default, but which is not usable for practical purposes. Let's have the coffee break. Let's reconvene in 20 minutes at 10:40. If you have more questions than that, I'm going to stay here, maybe walk to coffee, but feel free to ask me more questions about that if you need. Yeah.
Can I join to my desktop? Oh,
Yeah, you should be able to save because it's actually like one big HTML file. So if you save, I think it should work.
hi. When are going to talk about the load balancer and service mesh?
Soon. Yeah.
If we could speak about if we need some special scheduling or load balancer logic. Let's say I have a use case when, let's say I'm going to launch several pods, but when I submit the task to the pods, I want to take into place the scheduler policy to which pod exactly I will be submitting task. I'm not sure if Kubernetes is right for this, but just to think it's possible.
So you, in that case, you want to load balance HTTP requests or more like?
RPC requests.
Okay, so you have RPC and you want to route them to the best place.
Maybe I can ask Kubernetes to tell me where the pods are running and how many of them are available, and then to do additional service to the response.
That might be a good use case for a service mesh, but I don't want to give a blanket statement like that. But basically, so you would make a choice depending on whether the backend is loaded or not,
Yeah,
or
exactly. It's a stateful backend. I can't keep the states outside of the backend in some databases.
so yeah, a service mesh could be a good option to look at least to get some inspiration. If you look at Istio and Linkerd, they have things like that where instead of using the load balancing mechanism of Kubernetes, which is very simple, there will be this sidecar that we were talking about earlier that's going to intercept your connection to the service. And then it can do some pretty advanced logic like, okay, I'm going to, it's kind of maintaining metrics on the backends, and it can decide I'm going to send to the backend that has the least connections or the one that was responding the faster in the last few minutes, or et cetera, et cetera.
Service mesh.
Yeah. And some service meshes are independent of Kubernetes. But now they kind of work together, but you can also often deploy a service mesh without Kubernetes.
Thank you.
Okay, I have a question. We might get the token of the admin user. I tried to log into the dashboard, but I cannot connect to anything else.
Right.
How would I get the token of that admin user, which is created in the kubectl file?
So the admin user doesn't. Oh, you mean okay? User can resources. So there are a few ways to do that. The one way is to you give permissions to that user over there, like the stream system.
But that's the token that I'm using to log in with to sign up that secret.
Okay, I see. Okay. So, thinking about what is the easiest option, you could create another service account, like so you do like kubectl create service account, admin or whatever, and then you would grant privileges to that service account.
Okay, I see.
In the slides, normally there is no, it's in the YAML, but you could run a command like this, create cluster role binding, cluster role binding is an association between a user and a set of permissions. And then you would do like dash dash service account equal admin or whatever the name of the service account you created.
And I give access to like everything to that user.
And then this would, because system masters is the equivalent of root on a Kubernetes cluster.
Try that. Now, how do I get the token of that specific user after I create it?
So we would do that. Okay, we need to specify a name. So the name would be like admin can do everything. It's just like an arbitrary name for the binding. What did I forget? Sorry, my bad. The cluster role is cluster admin. Yeah. System masters is the equivalent of root, but the permissions corresponding to that is the cluster role, cluster admin. And service account, I need to put the namespace name. So this, then kubectl create service account. In the namespace kubesystem, I call it admin. And then if I want to get the token for that, I would do kubectl get secrets in kubesystem. And I would have one for, yeah, that would be admin token here that has been automatically created.
Can you leave that up so I can?
Sure.
So I just thought I'd ask a little bit more about my last question, which was about the about Weave. So it's actually kind of surprising to me that there's no default like network implementation. Or you said that there might be one, but it's like not that good.
So there is a default implementation. Like there are 3 plugins for network. The first one is kind of the no plugin. And in that case, when kubelet creates a container, it just creates the container and it doesn't care about the network. So in most cases, this will be okay, but if you only have one node, because it will create the container using the container engine. And so when you create a bunch of containers, generally they can communicate together, but if you have another node somewhere else, they just won't be able to communicate. The second plugin is called KubeNet. When you use KubeNet, you have to associate to each node a subnet, and then it's going to allocate addresses in that subnet. So you can manually say, okay, this node has this subnet, this node, this subnet, this node, this subnet. So you get a bunch of different subnets, and then you need to add bridging or routing or something to interconnect these things together. And then the third option is to use CNI, the Container Network Interface. And with CNI, basically each time that the kubelet needs to allocate an IP address or to configure the actual networking, then it's going to call a CNI plugin. And CNI plugins can do whatever they want. Virtually every Kubernetes cluster nowadays is using CNI, but that's where you have like many different CNI plugins available.
So what's the benefit of Weave? I'm just kind of curious now.
So the thing is that if you're on-prem, for instance, if you just like, you have a few machines in a rack, or like you're setting up a lab with actual switches, then you could use bridging, and that would be super simple. You could have like a DHCP server for the pods and bridging, and that's it. And that would be extremely straightforward. However, you can't do that on cloud because you can't do DHCP for containers in a cloud environment, and you don't have direct level 2 connectivity, so you can't do bridging. What you can do on some cloud providers is that you can tell them, okay, let arbitrary IP addresses circulate on the network fabric, but by default you can't even do that. Like, if I have a cloud instance and I change the IP address, like with ifconfig, it won't work. I can change the IP address, but then the packets will never will never be forwarded by the cloud provider. So that's why very quickly they were like, okay, we need something so that we can encapsulate the traffic between the pods inside packets bearing the normal IP addresses of the instances. And that's exactly what Weave is doing. It's using encapsulation. It's a little bit like a VPN if you want, but instead of being between two machines, it's between a bunch of machines. And instead of having like one VPN server, it's kind of smart. So let's say we both are nodes running containers, and I have a container wanting to send a packet here. It's going to be like, okay, like the container is going to just send the packet. The host will be like, okay, this is the packet coming from the container, going to another container. I'm going to look up where is that container. Oh, on this machine. So it's going to encapsulate that in a UDP packet. Send that UDP packet like node to node. So you, the node, you receive that packet, you can decapsulate that and forward it to the container. Okay.
Thank you.
I had turned it off. So
Yeah, that's
okay. It was just.
There we go.
Thanks. Yeah, I'm going to get coffee. All right. Let's resume for the second part. So I quickly looked at the questions that had been asked in the Gitter chat room. First, kind of logistics things, so about size of text here. I'm going to try to zoom more because indeed from the back of the room it's pretty hardcore to see what I'm typing. Almost all the commands that I type are in the slides in the gray rectangles. We have almost continuous integration on the slides that extracts the commands from the gray rectangles and copy pastes them into terminals to make sure everything works. So sometimes I deviate a little bit because I want to show alternate ways of doing things, but if at some point you can't see a command that I typed, you will see a command that works in the slide themselves. But I'm going to try to zoom that enough so that you can see what's going on here. There was another question about like clarification of what exactly are services. Are there a little bit like elastic IPs on Amazon, for instance? I'm going to say kind of, but it's more like that. It's extremely hard to give a definition of services that would be simultaneously correct and also not kind of eye-rolling. We could say, oh, it's a static IP address for a pod. It's kind of easy to understand, but it's a gross simplification because it's not just that. A service can also give us load balancing, but sometimes there is just one pod, so there is nothing to balance. And it's not always about pods. Like sometimes a service can be used to access something that is not on a pod or that is even outside of the cluster. So that's why the only correct definition is stable endpoint for a network thing. But that's the kind of definition that lets us like, okay, what does that really mean? We're going, of course, to see examples of services and create our own, and I hope it will clear up any questions you might have. So it's time to run our first containers, now that we've seen a lot of theory and concepts and etc. And first things first, remember what we said earlier. So first, we can't run really a container. What we can run is a pod, and in that pod there will be a container. And again, we can't really run, we can't tell Kubernetes run something. All we can do is write a nice spec saying, I would like this thing to be running, send that to the API server, and then the API is going to store that in its CD, and then a bunch of controllers are going to wake up and make that happen. Okay, for the first example, we're going to do something fairly simple. I just want to run ping. So I want to have a ping in a container, like pinging an external address. And the syntax for that is going to be kubectl run. Then I have to give a name. So the name I'm going to give is ping pong, but it could be foo or ABC, like doesn't matter. Then I indicate the image, the container image that I want to use. So here I'm using Alpine, which is a tiny distro that's often super convenient for container workloads because it's so small, so it's fast to pull, etc., etc. And then I put the command I want to run, ping 1.1.1.1. So first I get like a deprecation warning. Let's pretend that this did not happen. I'm going to explain in a few minutes why it's here and what it means. And then I see deployment ping pong created. And remember, when we see that, it doesn't mean that our thing is running. It just means I've written the spec in etcd, and now I'm going to work on that. Now if I do kubectl get pods, I see that I have indeed a pod called ping pong yada yada, and it's running. It's 30 seconds old, so it seemed to be up and running. However, it's interesting because that pod is not named ping pong. It's named ping pong, and then there is a string here and another string there. And here it did not tell me like pod ping pong created. It told me deployment ping pong created. So to figure out like, okay, what exactly happened, I'm going to do kubectl get all, like show me everything. It's not exactly everything because a bunch of objects here are not shown, but at least I see that I have indeed a deployment named ping pong, and then I have a replica set named ping pong something, and then I have a pod named ping pong something and something more. So I created a deployment. That deployment created a replica set. That replica set created a pod. So at this point, we can wonder, like, why all these extra layers? Like, do we really need all that? So yeah, why do we need all that? Because imagine that later I want to scale my things. I don't want just like one ping, I want multiple pings. Okay, for ping it doesn't make sense, but for a web service that would make sense. So if I just have a pod definition, in that pod definition I don't have any number, any scaling notion with that. So what I want is an object that is, I want that many pods like this specification. So I have a pod specification, and then I have something bigger than that, and that thing bigger than that is a replica set. A replica set is a pod specification and a number. So the replica set will help me to scale things fairly easily. But if I just have a replica set, to simplify things a little bit, we could say the mission of the replica set is to make sure that I have that many pods with that specification. So let's say I create a replica set saying I want 5 pods pinging 1.1.1.1. And then I change my mind. I say I want to ping 2.2.2.2. So I update the definition of the replica set. So suddenly the mission of the replica set is to make sure I have 5 pods pinging 2.2.2.2. And at that point, the replica set had its eyes on the pods pinging 1.1.1.1 and making sure, like, okay, if a pod goes away, I'm going to restart it. If I have too many pods, I'm going to remove the extra ones, etc. So this replica set was seeing 5 pods running the right thing and everything was fine. Suddenly, I changed the replica set. Suddenly, the replica set doesn't see 5 pods, it sees 0 pods, and it's like, oh, panic, and it's creating 5 new pods with the new definition. If you find the ping example a little bit silly, imagine that we're talking about the version of the code that we've deployed. So I'm deploying v5, and then I want to deploy v6, and so when I update my replica set, suddenly the replica set is kind of lost. It's like, okay, I need to recreate all the pods. That's typically not what we want. We want to do a progressive and smooth rollout where we update the pods one by one, or at least like by groups in a progressive way. So to do that, instead of just updating the replica set and having everything happen in chaos, what we will do is that we will have 2 replica sets, one corresponding to the old version, one corresponding to the new version, and we are going to do a kind of fade in, fade out. So I'm going to, okay, let's say this is old version, this is new version. So I'm going to scale down the old version while I scale up the new version. A little bit like a DJ mixing 2 tracks, basically. And so to coordinate that, I'm going to have another object sitting on top, and that object is the deployment. So what really happens is that when I create a deployment, it's going to create a replica set corresponding to the version that I want to deploy, and that replica set is going to create a pod. Now, later, when I want to update these pods, I update the deployment object, and what it's going to do is create a new replica set and then do that scale down, scale up in parallel. So that's why we have these 3 layers: pod, replica set, and deployment. Each of them adds something. Right. So supposedly we are running a pod that's pinging some IP address. How do we confirm that this is working correctly? I'm going to do kubectl logs, and then I give the name of a pod. I can't do just kubectl logs ping pong, because ping pong is not a pod, it's a deployment. So if I do that, it's telling me pods ping pong not found. I have to put the name of the pod, which in my case happens to be this. Here I use the completion. I just hit tab and it completed to the only pod matching that, but I could also copy paste the pod ID. So when I do that, I get the output of my ping command. So far so good. And another option I have is to do kubectl logs deploy / ping pong. In that case, it's going to be like, okay, let's look up that deployment ping pong, deploy ping pong or deployment ping pong. That's the same thing. Deploy is just a short version of deployment. So it's going to figure out, okay, what are the pods corresponding to that deployment and show me the same output. Okay. Right. If I want, I can also use --tail and indicate how many lines I want to see. 3 lines is good enough. I can also add --follow and have the equivalent of a tail -f. In that case, it's going to stream the logs of that pod for me. Great. Now the next step is that I want to scale this deployment. I don't want just one pod doing that ping, I want multiple pods. So I do kubectl scale. What do I want to scale? A deployment. Which one? Ping pong. How? With replicas. And I want 3 replicas. It's telling me immediately, yep, done. But again, that just means that it has stored the new spec in etcd. And then the controllers wake up and create the pods and push them to the kubelets. And now here, look, if I run the kubectl logs command again, I'm going to have a little line of information on top telling me I found 3 pods, and I'm going to show you the output of that specific one. So it's not showing me the logs of multiple pods at the same time. Okay. The replica set is making sure that my pods keep running. So for instance, if I do kubectl get pods, and I decide to destroy one of these pods, so I'm going to do something a little bit fancy here. I'm going to split my screen. And here I'm going to do kubectl get pods, and I'm going to add --watch, or -w in short, which means show me the output of that command, and then keep looking at these objects and show me if anything moves. Now I'm going to do kubectl delete pod, and I'm going to put the name of one of these pods here. When I do that, I see that my pod will be terminating like immediately, and instantly the replica set, whose job is to make sure I have exactly 3 pods doing that ping, the replica set is like, ooh, problem, we only have 2 pods matching this spec, so I'm creating a 3rd pod right away to replace the one that was destroyed. And 3 seconds later, the replacement pod is up and running. This is the sometimes we call that like the self-healing features of Kubernetes. One of the points of using Kubernetes is to make sure that we have that many replicas up and running at any given point and automatically restart pods or containers when needed. That's the kind of thing we can also achieve with auto-scaling groups, for instance, on Amazon. That's the equivalent of using, for instance, supervisor to make sure that one process is always up and running, but on a cluster. So it's not just making sure that one process is running on the machine, but making sure that 3 copies of this container are running across the cluster. Right. So now let's go back. I said, oh, there is a deprecation warning when we did kubectl run. Let's revisit that. If I wanted, I could add some flags to kubectl run. For instance, I could do kubectl run --restart never, and in that case, it would not create a deployment. In that case, it would really give me just a pod, because if I say --restart never, It means I don't care about automatically restarting and scaling, etc. I just want a one-shot container. So in that case, kubectl run is like, okay, I'm going to give you just a stray pod. I can also use kubectl run -- schedule, and then I can pass a cron style schedule. So that would be something like this, -- schedule. You know, it's the 5 fields of a cron tab, and this would mean, and then I would put like whatever here. The thing I would put behind would be run every minute on the cluster. So that means that depending on the exact flags and combination of flags I'm passing to kubectl run, sometimes it would create a deployment, sometimes it would create a pod, sometimes it would create a cron job, etc., etc. And this can be kind of confusing. And so there was the decision a while ago to say, okay, let's stop with this kind of pseudo magic where you have to know which combination of flags do what, and instead let's be explicit about things. Explicit is better than implicit. So if we want to create a deployment, we use kubectl create deployment. If we want to create a job, we do kubectl create job. If we want to, etc., etc., etc. And eventually, at some point, kubectl run would be repurposed so that it just runs a one-off job, a little bit like Docker run. So that's why we got that deprecation warning. I'm still using kubectl run like for the first thing that we want to run because it's simpler. But in the future, we will almost never use kubectl run again. So what are the various options we have to run things? We have kubectl run, which is great when getting started because it's pretty close to Docker run, for instance, and it can create a bunch of different things. Then we have kubectl create and then a resource type like kubectl create deployment, for instance. That one is fairly easy to understand. Like when you look at the script doing that, it's fairly easy to understand what's happening. But it won't let you create everything. Like there are some resources that you won't be able to create with kubectl create. And then finally, we have kubectl create -f or kubectl apply -f that both take a YAML file, and the YAML file contains a resource specification, and then we can pass absolutely whatever we want because that YAML spec can be arbitrary. So if there is a new type of object tomorrow and I want to create that, I don't need to wait for a special command like kubectl create Elasticsearch cluster. I could write the YAML specification for that and then use kubectl create -f my YAML file. Right. Okay, back to logs. We have on our pods, if I use, for instance, kubectl describe pods on one of my ping pong pods, I see that on my pods I have labels. In particular, I have a label run equal ping pong. When I use kubectl run to create something, there will be a run label with the name of the object. So if I do kubectl run ABC123, then there will be a label run equal ABC123. So I can use that label when I use commands. So for instance, I can do kubectl get pods -l, like labels, run equal ping pong. And that shows me only the pods with that specific label. Virtually every command that can manipulate objects can use selectors. So for instance, earlier, when I used delete, I could do kubectl delete pods with that label, and it would delete all of them. Later, we will see other commands like kubectl label to manipulate the labels themselves. Same thing, we can use these commands. Same thing with kubectl logs. I can do kubectl logs, and I say, okay, show me the logs of all the pods that have this label. And now I'm seeing not just the logs of one pod, but all the pods of this deployment. It's not really a nice way to consume this information, because here I don't see which pod sent which log line, so it's not so great, but it's a good starting point. I can use, for instance, --tail1, so show me the last line of log of each pod. So since I have 3 pods, I get 3 lines. And I can also use --follow, and then it's going to stream in parallel all the logs of these pods. This, like combining streaming and a selector, only works since very recent versions of Kubernetes. Why? Let me show you why. I'm going to scale up my ping a little bit more. So I'm going to do kubectl scale deployment ping pong. How many replicas? Let's say 10. And then I'm going to run the kubectl logs command again. And now it's telling me, no, I can't do that because there are 10 log streams and I will only do 5. Why? Because when we are streaming logs, for each log stream, we are opening a separate connection to the API server, and then the API server in turn is opening a connection to the kubelet that is responsible for that pod. So now if I do that with 10 pods, it's opening like 10 connections to the API server, and for each of these connections, like 1 more connections to the node running that pod. So this is why it's only a recent option. Like in older versions of kubectl, it was like, no, we're not going to do anything fancy like that. It's like 1 stream at a time. And then when the option was added, we were like, if I have a big cluster with like thousands of pods, and I fumble a little bit, and I end up passing a selector that selects 1,000 pods, I'm going to open 1,000 connections to the API server, and the API server is probably going to not feel great about that. So that's why there is this limit of 5 by default. Now if I know what I'm doing, I can say, hey, max log requests equal 100, and now it's going to stream me all these things at the same time. Still, even with recent versions of kubectl, that's not great, because I'm not seeing which pod is sending which line of output. So I'm going to give you an extra tool that is great to have like streams of logs. That's Stern. So that's not part of Kubernetes. It's a third-party external thing. It's a Go program, which means that you just have to download that binary, and it's available for Linux, Mac, Windows, and you just download the binary and that's it. And when you do Stern, you can pass it either a selector, so again like -l run equal ping pong, and it's going to stream all these logs. Okay, it's catching up. Yeah. And now when it streams the logs, we get something that reminds us a little bit of Compose. So I have the name of the pod, and then the name of the container within the pod, and then the output, and a nice set of colors here, which will turns out to be convenient in a little moment. All right, another advantage of Stern is that if I scale up or down, it's going to keep track of new pods coming up and coming down. So for instance, if I do kubectl scale deployment ping pong -- replicas 12, you're going to see here, okay, that was really fast, but you see like plus here, so it detected, oh, we have new pods matching that, so we're going to dynamically attach and show the stream. And one last thing about Stern is that if I'm super lazy, I don't even want to find out the selector of my pods, I can pass a string, and it's going to be handled as a regex against pod names. So for instance, if I do Stern ping, it's going to match all the pods with ping in the name and show them to me. Of course, that's fairly dangerous, because if I do Stern dot, it's going to show me the logs of all the pods. So we have to keep in mind, each time it's opening one connection to the API server. So on a big production cluster, if you do that, the people responsible for the clusters might have feelings about it, but it's available if necessary. Okay. Streaming logs, shortcomings of kubectl logs. Before moving on, yeah?
What's the namespace that you created those pods?
What's the namespace where we created these pods? By default, the namespace is default.
Okay.
So for instance, if I were to use the kubectl get pods -- all namespaces, then I would see all my kube system pods, and then the ping pong pods are in default. Okay. And while I'm here, just to simplify things a little bit, I'm going to scale down ping pong to 2 pods so that when I display resources, etc., we're not getting pages and pages of useless ping pong pods. If you're worried about are we basically flooding 1.1.1.1, don't worry, it's designed, well, not specifically for that purpose, but it's been designed to withstand random streams of traffic. So nobody is waking up right now in the middle of the night somewhere wondering why there are like 70 people sending a bunch of ping packets to that address. Right. Questions? Yes.
Can you show the command for stern showing the different one more time?
So the command I use for stern so I could use just like a substring, and then it will do a match, or I can do -l and then a label expression, like run ping pong. Note that -l can also be --selector. That's the same thing. Okay, yeah.
Is the label run equals to on your label if that deployment was made by the runner?
Is that label available only for kubectl run? Right, so in that case, when I do kubectl run foo, it's going to put a label run equal foo. If I use kubectl create deployment foo, the label is going to be app equal foo. It's just a convention in the kubectl commands. Yeah? If I create a job, or right, if I do kubectl create job, the job object, or if I do kubectl run -- restart on failure, the job object is going to create a pod, and it's going to let's say monitor that pod. If the pod exits with a 0 status code, meaning all good, then the job object is going to be like, okay, perfect, great. But if the pod exits with a non-zero status code, or if it gets killed by a signal, or if it goes out of memory, or if the node goes away and the pod goes away, then the job is going to recreate that pod until it completes successfully. That will be the difference between a job and a pod. Right. Okay, so we've been sending pings around. That's fun, but we would like to have something that has more of a purpose. We would like something that can serve network traffic, and that will be the opportunity to revisit services and hopefully really figure them out this time. So we want to, we are going to create a little web service, and then we will expose it so that we can connect to that service. We have different types of services depending on basically where the traffic comes from. So we have cluster IP services, which are purely internal services, just like the Kubernetes service that we saw a little bit earlier. It just has like a cluster IP and that's it. So this is purely internal communication. Then we have node port. Node port is a kind of basic building block for external communication. When I create a node port service, I still have a cluster IP that I can use internally, but I also get a node port. So it's a port between 30,000 and 32,768 allocated for my service. And then when I connect to any of my 4 nodes, it will, on that node port number, it will send me to my service. So for instance, for the web UI, when we will want to connect to that, we will create a node port. A port number will be allocated at random, maybe like 30,123. And then if I connect to one node on 30,123, I will get the web UI. Then we have 2 more service types, load balancer and external name. Load balancer is used when we want a cloud load balancer like an ELB or GLB. Just to dispel a doubt, if I want to load balance traffic, I don't need a load balancer service. Any service will do load balancing if I have multiple pods behind it. So load balancer is only for a cloud load balancer. The point of this is if I want to expose a service on a specific port, not something like 30,000 whatever, but like port 80 or port 443 or port 22 for SSH or Git, then I will create a load balancer service. Then Kubernetes is going to make some API calls to my cloud infrastructure that will create a cloud load balancer, and that cloud load balancer will send traffic to the pods behind it. And finally, we have external name, which just sets a DNS alias so we can safely ignore it for now. Okay, so for our first example of a service, we are going to run an image called jpetazzo/http-env. You will see many examples, like on Kubernetes, using just Nginx, because it gives us a nice and easy and simple web server. The only downside of Nginx is that it will give us a welcome to Nginx page, and if we put load balancing, all the backends give us the same welcome to Nginx page. So this http-env little service will show its environment, including the host name, and so that will show us which pod served the response. Right, so I'm going to do kubectl create deployment. I will call that http-env, and then I have to indicate which image I want to use. So image jpetazzo http-env. That's it. And then I'm going to expose that deployment. So basically create a service. So kubectl expose, what do I want to expose? A deployment. Which one? http-env. And if I do that, it's going to tell me, hey, what's the port number that you want to use? And so I have to tell which port. And in that case, my http-env service is listening on port 8888. So when I do that, the same way that kubectl run and kubectl create deployment are basically writing a YAML specification for me and sending the specification to the API server, kubectl expose is writing a YAML specification for a service and sending that specification to the API server. So now that I've done that, if I do kubectl get services, in addition to Kubernetes, I see http-env, and you see there is like a cluster IP that has been allocated. So I'm going to curl that. If I curl it like this, it's going to hit port 80, so it's going to just time out, because again, my service is on port 8888. So let's add the port number. And it's sending me the environment of the server as a JSON map. The only field that is of interest to me is the host name, because it's telling me the host name of the pod. See, like host name, http-env, 599, etc., 9p8zb. If I do kubectl get pods, I have indeed a pod with that very name. Okay, so I can repeatedly curl that, and I see that since I only have one pod, all my responses come from that. So next, I want to scale up this deployment. So kubectl scale deployment HTTP env -- replicas, and I'm going to put like 3 replicas, and then I'm going to do my curl command again. So we see now the hostname environment variable will change over time. Since that's JSON, I can use JQ, which I was mentioning earlier, to extract just the field I want. Like, give me the field hostname. So I do curl pipe JQ.hostname. Since I don't want to have like the extra output of curl, I'm going to add curl-s, like silent. So now I see like which backend is serving this the request. So what kind of load balancing are we using? Well, to find out, I'm going to send a bunch of requests. So let's do a little for loop, like for I in sec20, do this. And then I look at the output, and I don't know if you see a pattern, but it doesn't seem to be round robin. It's not like it's not 1 2 3 1 2 3 1 2 3, like 9JG 9JJG 99. There is no pattern in it. There is no pattern in it because at this point it's using random load balancing. If you're curious about what's going on, you can dive into IP tables. I won't do it now because I won't need to stay on track. But what's happening here is that the kube proxy component, which I briefly mentioned this morning, is responsible for watching the services and the pods and creating a bunch of IP tables rules to intercept the traffic going to a cluster IP. And each time I create a connection to a cluster IP, it's going to pick a backend at random and rewrite the destination IP address using the IP address of one of the backend pods. This is an implementation detail. You don't have to worry about it. But if you wonder what's going on, that's what's going on. Question? Yeah. Sorry, I really can't hear you. Is there a way to get some metrics on that? Are you thinking about like network metrics or CPU metrics or all of the above? Everything? So there are some metrics that we can get there is something called the core metrics pipeline, which is something that is not required on all Kubernetes clusters. So it will work on some, not on others, but it's basically kubectl top. And you can do kubectl top nodes. It's going to show you CPU and memory usage across the nodes, or kubectl top pods, and it's going to show you like same thing but for pods. But again, this requires the metrics server to be installed, which has been done on these clusters, but maybe not on all clusters. Now, if you want like more insights, you will need to install, for instance, Prometheus. And then Prometheus will be able to scrape metrics for all the nodes and also the pods and at the container level, etc., and aggregate all that. If I'm not going to talk about Prometheus this morning, but if you look on container.training in longer workshops, there will be a chapter on Prometheus. Yeah. And just to wrap up, if you want metrics on the network level, often people will advise, hey, look at service meshes, because that way you will be able to monitor like latency to services and that kind of thing. It's not the only way to do it, but it's a really popular way to do that on Kubernetes clusters. Okay, so we ran a simple HTTP service on the cluster. We exposed it. Here I'm repeating that services are layer 4 constructs, which is really a fancy way to say that, yeah, I can curl that thing, but I can't ping it, and I can't curl a different port. Right. So that was our first exposed service. Other questions before I move to the next thing? So you see in that case that the service it's a load balancer. But I don't want to say a service is a load balancer, because if I only have one pod, then it's not load balancing anything. And I don't want to say that it's a load balancer for pods, because a service could also send traffic somewhere else, like outside of the server. It provides an abstraction. So for instance, right now, when I connect to this IP address over there, it's load balancing traffic to pods. But if I wanted, I could handcraft a service that would send connections to something else completely outside of the cluster. So again, a service is a stable endpoint for things. Okay, so now we want to run Docker coins on the cluster. For that, we will need to ship images. Why do we need to ship images? Maybe you've heard like the Docker tagline, like build, ship, and run any app anywhere. Early this morning, we did build and run, like we built container images and we ran them. We didn't need to ship anything because we built and ran on the same machine. So it's like ship to the same place. But now we have multiple nodes, so we need to ship things around. We need to have the same images on all the nodes of the cluster, so we need to ship these images, and the easiest way is to use a container registry. So what we're going to do is that we're going to reference images for Docker coins. We're going to use images named dockercoins/walker, dockercoins/hasher, dockercoins/rng, etc., etc. Now, a little bit of details of how do container registry work exactly. When we run an image like Alpine, for instance, like we did earlier, or Redis, this is going to expand into library/Alpine. Library is a special user on the registry. Now, if I just have library/Alpine or jpetazo/http-env, this means an image that is on the Docker Hub. And so it's going to expand into index.docker.io/library/Alpine. And so likewise, we could access images on different registries. For instance, if I want the Alpine image, but with bash instead of a really minimal shell, I could use gcr.io, so that's the Google Container Registry, /Google Containers /Alpine with bash. Okay. So the plan to run Docker coins on Kubernetes is first, I'm sidestepping the build issue. I assume that somebody has built the Docker coins image for me. Somebody that could be for someone else who built and then pushed the image, or maybe I've set up some automated build. We consider that's a solved thing. I have images on a registry. So I'm going to create one deployment for each container. So one deployment for Hasher, Redis, RNG, etc. And then I'm going to expose the ones that need to receive traffic. So for the Redis container, I can use the Redis image. And for the other containers, the images that I have are all called Docker coins / the name of the service, :v0.1. So that means Docker coins / hasher :v0.1, Docker coins / walker :v0.1, etc., etc. Right. So we're going to do that. That's the recap for the 4 image names. In the slide here that follows, I'm using a little for loop, and that for loop assumes that you have set the registry and tag environment variables. Sorry, that's maybe a little small from the back of the room, so you can just follow the commands that I'm going to run on screen. First, let's do the easy one, the Redis deployment. So I do kubectl create deployment Redis, and I indicate the image I want to use, which is --image Redis. Done. Then I want to create the 4 other containers. So create deployment walker, dash dash image equal docker coins / walker colon v0.1. And then I do the same for the 3 others. So hasher, web UI, and RNG. Oops. And I'm going to give everyone a minute to run all that. Yeah.
Is the order that we start these important?
Is the order important? No, at this point it's not, because the worker is going to try to connect right away to the other ones. But the order is not important because as long as we haven't created the services, the worker won't be able to connect to anything. So at this point, what's going on? Well, let's have a look. I'm going to do kubectl logs deploy / RNG, for instance. And this is going to tell me, like, that's just the output of my RNG container. It says, yep, I'm up and running and listening on port 80. Same thing for hasher, like, yep, I'm up and running and listening on port 80. However, if I check the logs of the worker, spoiler alert, I get pages and pages of tracebacks telling me error connecting to Redis, name does not resolve. That's because I haven't exposed yet Redis. So if I want that to work, I need to expose Redis. For that, I do kubectl expose. What do I want to expose? A deployment. Which one? Redis. When I do that, it's going to tell me, hey, I need the port number. Okay, what's the port number? Even if I don't remember which port is used by Redis, I get a nice convenient reminder just here by my Python traceback. So I need to expose Redis on port 6379. Okay, so it says service Redis exposed. Let's have a look now at the logs of the worker. And in fact, I'm going to put these logs in a separate pane here. Okay, now I get a slightly different error. It's telling me name does not resolve, but now that's for host equal RNG. Because yeah, I haven't exposed RNG yet, so I need to do the same thing. I need to do kubectl expose deployment RNG. On which port? Well, that one is on port 80. So I do that. And now it's telling me that it can't connect to hasher. So I need to expose hasher as well. And for each service that I create, I get a DNS entry mapping that service to its cluster IP. That's why the code works. Like when it's trying to connect to Redis, when I create service Redis, it's adding a DNS entry mapping Redis to 10.105.158.51. So doing the same dynamic DNS thing that we had early this morning with Compose. And now that I have created all the relevant services, my worker code is happily doing its infinite loop, generating random data, hashing it, etc., etc. Yep.
Can you also avoid using fixed ports?
Can I avoid using fixed port? Do you have a specific example in mind? Like,
Running in a cluster, I don't know if another application used port 80.
oh, okay. So if what if I'm already using port 80 or port? So here it's important to know that I'm not using port 6379 on the whole cluster. I'm just using that on this cluster IP. So it means I can have as many services I want using the same port because each of them gets its own cluster IP. For instance, here I have both Hasher and RNG using port 80, but since they each get their own cluster IP, that's fine. I don't get a conflict. I can see here, like if I do get SVC, I see like Hasher port 80, RNG port 80, but they both use different cluster IPs. So I'm good. Okay, now I would like to see the web UI. So I need to also expose the web UI. But when exposing the web UI, I want to make it available from outside. So I'm going to add a -- type node port. So now if I do kubectl get SVC, web UI, please. There we go. Now in the ports column, I see port 80 has been exposed as 32190. So now I can go back to my web browser and I can connect to node 1 on 32, sorry, I forgot the port number already, 190. And that gives me the web UI that we had this morning. And I can connect to any of the 4 nodes on that port number, and it's going to route the connection to the pod that is running the web UI. Right, so we're back to square one, but now we're running on a cluster, so hopefully we can scale things and have fun. Right. So scaling that, with what we've seen earlier, it should be fairly straightforward. So as a reminder, it could be useful to understand how we really want to scale the app, because the command itself, we've seen it already, but we need to understand how are we going to scale Docker coins. If we look at the architecture of Docker coins, we have this worker doing an infinite loop, and then these web services around it. So if I start additional copies of the worker, I get like multiple things doing the infinite loop in parallel, so I should get more performance. Let's see if it adds up. I'm going to scale additional copies of the worker. So I will do kubectl scale deployment worker -- replicas 2. So a few seconds later, on the pane above, see, we saw like now we have brownish pods and purple pods. And if I look in the web UI at the same moment, I see that instead of having about 4 hashes per second, now I have about 8 hashes per second. So by doubling the number of workers, I doubled the speed of Docker coins. I'm going to repeat the same thing to get like 3 replicas. So same command, like kubectl scale deployment worker -- replicas 3. And okay, it picked another shade of purple, so it's not super visible above. But if I look here in the web UI, I see that indeed we seem to be going faster. So we might think, okay, I'm just going to put like 10 replicas, and I'm gonna get like many Docker coins, and we can all go home and say, wait, we learned to scale things. Unfortunately, if I look at the web UI now, it looks like it's slowing down. It's going back to 10 hashes per second. Without diving into too much details, but here it was not really going to 12 per second. On average, it was at 10, but it was doing like 12 and then 8 and then 12 and then 8. That's why you can see like peaks and throughs, but really on average, we were at 10 per second, and we cannot go higher than 10 per second because we have a bottleneck somewhere. So let's try to find out where that bottleneck is. And to do that, if we were, if this were like actual production code, we would have some instrumentation and we would be able to see like latency and whatnot. But if we were to look at the code, we would see that it's like 2 Python scripts in the trench code. So we have to use other tools to find out what's going on. So I'm going to use HTTP ping. HTTP ping is just like ping, but for HTTP services. So it sends a really simple GET request and sees how long it takes. So I'm going to go to the next pane, zoom a little bit so that everybody can see what's going on. kubectl get services. I want hasher and I want RNG. So hasher is on that cluster IP, so I'm going to do HTTP ping on that cluster IP. And I see that hasher takes like a couple of milliseconds to reply. Okay, that seems normal. Now let's look at RNG. I'm going to do HTTP ping on RNG. 800 milliseconds for a local web service, that's slow. So immediately we can guess something's wrong with the RNG service. So we can think about, okay, why is RNG slower? Like, what does justify that for a local web service, it takes almost 1 second to reply? So by chatting with some coworkers around the coffee machine, somebody will say, oh, that's probably because of entropy. Entropy is that thing that is used to generate random numbers on modern computers. We need an actual source of randomness. If that, you can imagine, it's a little bit as if somebody was throwing dices like in the kernel constantly and writing down the numbers on papers. And when you have something that needs strong random numbers, they just say, hey, give me some random numbers, and they get a bunch of pages with random numbers. But if you are out of random numbers, because the person writing down, like throwing dice and writing down the results, if that thing is too slow, then you have to wait for your random numbers to come in. This is why if you're using something like PGP or GPG, when you generate strong crypto keys, it can ask you, now please move the mouse. And you're like, what? Because while you move the mouse, you're generating some randomness that gets collected by the system, and that helps to generate your random key. So here we're going to guess RNG is slow because of that entropy thing. And so the solution to make it go faster is to scale it, but not just scale it like give me, I have 4 nodes, so not just like give me 4 replicas, because nothing guarantees that my replicas will be nicely spread out on the cluster. I want something that will guarantee that I have exactly 1 copy per node. By the way, that explication is complete, excuse my French, bullshit, but it's a good pretext to introduce another way to scale things on Kubernetes. The problem is not entropy. So we're going to introduce daemon sets, and in the process see a lot of interesting things in Kubernetes. Just to make it clear, in the real world, it's extremely rare to use daemon sets for application workloads, but more on that in a moment. Okay, so we want to make sure that we get 1 copy of RNG on each node of the cluster. That's exactly what a daemon set will give us. And in fact, we have met daemon sets before. Remember when we were looking at the list of pods in kube system, we had 4 kube proxy pods and 4 weave pods. And when I used -o wide, we were able to see that the kube proxy pods were 1 on each node, 1, 2, 3, 4. Same thing for WeaveNet. These things are created by a daemon set. If I do kubectl get daemon sets, I see that indeed I have a kube proxy daemon set and a WeaveNet daemon set. This is extremely convenient because it means that when a node joins the cluster, automatically it will receive a kube proxy and a withnet pod. So automatically these network components will be scheduled and started on the node without me, cluster administrator, having to do anything with it. Okay. Unfortunately, we don't have a kubectl create daemon set command, at least not in kube 114. So we cannot create a daemon set in a nice way. So we have to fall back to plan B, which is write custom YAML and send that YAML to the API server. So how do we do that? Well, we read the documentation and we write the YAML, except I don't feel like reading documentation this morning. So instead, we're going to try to find our way around that. We're going to get a YAML that hopefully is close enough and see if we can twist it a little bit to get what we want. I'm going to get the YAML of the RNG deployment, since it's already creating pods for RNG, and see if I can turn that into a daemon set. So how do I get the YAML for an object? Well, we saw this already. It's with kubectl get-oyaml. So I'm going to do kubectl get deployment RNG -oyaml and send that to rng.yaml, for instance. And then I'm going to edit that YAML file and see what it takes to transform a deployment into a daemon set. So, first line API version, second line kind deployment. Well, we're gonna transform that deployment in daemon set. Pay attention to the capitalization, it matters. And then there are other things, but I don't feel like reading more YAML. So I'm just going to save and try to load that YAML with kubectl create -f rng.yaml. And it's going to give me exactly one screen full of errors, error validating data, unknown field, progress deadline seconds, etc., etc. Of course, like it couldn't be that easy. I can't just cast a resource type into another and hope that it would work. But if I look a little bit more in the error message, I see like unknown field replicas. Okay, that makes sense because in a deployment, I say how many replicas I want. In a daemon set, I don't say how many replicas. The number of replicas is exactly one per node. So that it makes sense that I wouldn't have a replicas field. I have another bunch of errors like unknown field last update time, missing required field that. And at the end it says if you choose to ignore these errors, turn validation off with --validate equal false. That seems like a good idea, and so far nothing bad happened. So by turning on validation, did I just break my cluster or do anything bad? No. Good news, that the job of the API server is also to make sure that it does not accept things that would completely corrupt or do horrible things to the cluster. I mean, don't get me wrong, I can still do horrible things. Like I could say, oh, give me 1 million replicas. That maybe something bad could happen if I were to do that. But I can't corrupt my cluster by sending invalid YAML. In that case, when I turned off validation, what it did was drop all the extra fields. All the fields that it doesn't know, goodbye. And then there are a bunch of required fields. Well, it tried to use default values. And if at the end the result is a valid YAML, then that's fine. Turns out that it's the case. After removing the extraneous fields, providing default values for the missing ones, we get a perfectly good YAML file and we can use it. So before going farther, I'm going to have a look at the web UI, and interestingly, now instead of being stuck at 10 hashes per second, we are at 20, 30 hashes per second. So what we did definitely had an effect. Maybe we have more pods or something happened, and now the app is faster. which is really interesting because if we think about it, okay, maybe I created more pods. Let's check. kubectl get pods. Lots and lots and lots of things here, but you can see in the middle I have multiple RNG pods. So I created additional pods. And you see they are slightly different. This one has a longer name. That's the pod created by the deployment. And these ones have shorter names. They are the ones created by the daemon set. So we created pods. That's great. But somehow, by some magic, the pods were added to the load balancer. Because if the app is going faster, it's because like these pods are in use right now. In fact, I would like to see the logs of these pods. So I'm going to do stern RNG. And stern RNG is going to, so yeah, you can see like if I freeze that for a second, the red one here, that's the pod belonging to the deployment, and the short ones are the pods belonging to the daemon set, and everybody is serving traffic. Interesting. I kind of wonder why. And here, to try and find out, well, first, I don't know what you think, but this list is really long. So I would like to see only the pods belonging to RNG. So one option would be kubectl get pods pipe grep RNG. Or another option would be to use a selector. Remember, like we said, I can do kubectl get pods -- selector or -l. Remember when I said if we do kubectl create deployment, it's going to put a label called app. So I can do kubectl get pods -- selector equal app equal RNG. And that shows me all the pods with app equal RNG. And that gives us a hint about how do these pods receive traffic. To get another hint, I'm going to look at the service RNG. I'm going to do kubectl describe service RNG. In the output, I see that my service has a label app equal RNG, and it also has a selector app equal RNG. That selector here, you can think of that as a live query on my pods, indicating which pods should be targeted by this service. That means which pods should receive traffic for this service. And here in endpoints, I get the result of that query, if you will. It's a little bit as if this were a software-defined load balancer, where the backends, the endpoints, are select host port from pods where app equal RNG. Right. So now the last missing piece of the puzzle. Okay, so the graph is going higher because I have more backends in the RNG service. I have more backends in the RNG service because the RNG service is sending traffic to all the pods that have app equal RNG, and all the pods that were created by the daemon set have app equal RNG. But the last piece of the puzzle is, why do they have app equal RNG? I did not do like kubectl create with them. I just took the YAML of the deployment and tweaked it, and that's the reason why. Because in the YAML of the deployment, if I scroll down more and more and more, I have the template. So that's the template of the pods created. And I have labels app RNG. So all the pods created by the deployment and also all the pods created by the daemon set have app equal RNG. Right. So that's why this kind of automatically worked without us consciously adding these things to the load balancer. Right. One other little detail is that if I look at my resources, like if I do kubectl get, let's say, deployment and daemon set, like this, I see that I indeed have a daemon set called RNG, and I still have a deployment called RNG. When I used my YAML to create the daemon set, this did not destroy the RNG deployment. The RNG deployment still exists, which means that I can have multiple objects with the same name, RNG, but different types. And that was already the case before, because I have a deployment hasher and a service hasher. I have a deployment RNG and a service RNG and a daemon set RNG, etc. Right. Another thing is that, okay, so the goal of the daemon set is to create one pod per node. One pod per node. Let's look again at the RNG pods. I have 4 pods and I have 4 nodes, but if I look again, I'm going to use -o wide to see on which node they are running. I could naively expect to have one pod on node 1, node 2, node 3, node 4. And yet, I have node 2, node 2, node 3, node 4. So what's going on here? There are 2 things at play here. The first one is that node 1 is special. Node 1 is where the control plane is running, and it's using a special mechanism to say, okay, node 1 is the master node, and it should not receive pods like normal application pods. That way, even if I do if I make some mistake and I create 1 million pods, they won't go to node 1, and node 1 will keep running, so I can still access the control plane and I can still fix my mistakes. So, okay, that's why I don't have a pod on node 1. Now, why do I have 2 pods on node 2? That's because the daemon set is creating 1 pod per node, except node 1, but it's also not looking at the pods created by the deployment. So when it counts like 1 pod per node, it's not counting the pod created by the deployment. The kind of under the hood reason for that is explained a little bit further. There will be one of the extra detailed slides explaining why the deployment and daemon sets are using distinct sets of pods, if that's the kind of question that would prevent you from sleeping at night. Questions? Yeah.
So for the registries, how do we set up a private registry?
How do we set up a private registry? There are short and long answers. Let me try to condense things. If you want an example that you could kind of walk like step by step, if you look on container.training on the self-paced version, like basically the super long version of this, there is a lab where we are going to use a private registry running on the cluster and use that private registry. But it's also not a really realistic example because it's just using the basic registry without authentication, without anything, etc. So if we want a realistic example, I could have like two ways. One way is when I want a private registry because I don't want my images to be public. In that case, I could still use a third-party registry like Quay or Docker Hub or something like that. So I would create an account there, maybe give them some money because for private images, usually they require that. Then I would create a special object called a secret, and that secret would hold the credentials to access that registry. And then when I would create the deployment, I would say, hey, to get the image from the registry, I need to use this secret that I just created. You can see that like when I do kubectl create secret, there is a subcommand here for Docker registries. And when we do kubectl create deployment, in the many flags that we have, okay, I'm not seeing it here, but somewhere in there I have a flag to say use these credentials to pull the image. So that's one option. The other option is, well, I want private registry as in the image stays entirely within my control. In that case, I again choose your adventure. I have 2 branches. If I'm on cloud, I will typically use a registry backed by my cloud provider. So each big cloud provider will have one, like ECR on Amazon, GCR on Google Cloud, etc., etc. And then I will be able to use that registry. So I will create a registry instance using the API of the cloud provider, and then I will be able to push images there, or even have the cloud use some automated build from my repo straight to the registry. So that's one option. And finally, if I'm like, well, I'm on my own machines, I'm not even using a cloud provider, then that's the most complex option, because then I will have to run my own registry. And so either I go the commercial route and I buy something from Quay, or I get like Tectonic or Docker Enterprise, etc., or I build it myself with open source components. So in that case, I typically get the registry container image, which provides like just the REST API, but no authentication, etc. And then I add other components on top of that to provide replication and caching and authentication, etc., etc. Yeah.
Do we have at least two machines for running Kubernetes, since you mentioned that we don't run parts on the master node?
I didn't hear entirely something about not running on the master node.
We don't run parts on master node, you mentioned.
Right.
Yeah, so does that mean we have to have at least two machines for running Kubernetes?
Right, good questions. Since we don't run workloads on the master node, does that mean that we need to have at least two machines? The answer is it depends. If, for instance, if we are using something like Minikube or Docker Desktop or Micro K8s, which are like local Kubernetes deployment options, they won't have this mechanism in place. And so in that case, since I only have one node, I want to run everything together. Now, in a more production-like scenario, very often the don't run things on master nodes won't matter, because I will not have a master node. What I mean is that if I'm using a managed Kubernetes cluster, the control plane is running somewhere else. I don't have access to it. I just have like the API endpoint, and somebody else is running the control plane for me. And then I can't run pods on that because it's something else. For instance, there are many providers who are going to say, okay, I'm going to sell you like managed Kubernetes as a service. And what I'm going to do is that I'm going to set up one special Kubernetes cluster for me internally, and I'm going to run your Kubernetes control plane, of all my customers, on this Kubernetes cluster. So it's kind of running Kubernetes on Kubernetes in a way. And in that case, there is a bunch of nodes which are kind of your master nodes, but it's really a different cluster to which you have zero access and which is entirely managed by the provider.
So Kubernetes and a cluster node, every node is active. So every node share the.
Is it active for the control plane or for the workload nodes? So for the workload, all the nodes are active at the same time, and all the nodes can run pods at the same time. And so when one node goes down, there's going to have like two steps. The first step is that very quickly, like within 1 minute, the node will be marked as not ready.
So we to find which node is master node.
Well, how do we find out which node is a master node? There is no absolute answer to that. In this specific case, because we deployed the clusters in a certain way, then we do have a node that is dedicated to the control plane. But there are clusters where there won't be such a node because the control plane is somewhere else. There are nodes where I will have 3 nodes or even 5 nodes for the control plane. It really depends.
This means there's no master node. Every node is master.
It depends how the cluster was deployed, really. Yeah.
So I tried to do this. I tried to dump the YAML for the daemon set, and then delete the RNG deployment and the daemon set, and then reapply the daemon set here. But it didn't work. Can you do that directly?
Okay, good question. So this is, if I understood correctly, you try to dump the YAML for the daemon set. So -o YAML, and I'm going to put that into rngds.yaml. Then you destroyed the deployment RNG. And then you destroyed the daemon set RNG. And then you try to recreate the daemon set using the YAML that we just dumped earlier. And then you said it didn't work. So when we do that, let's look at the pods. Normally I should see 3, okay, I see a little bit more. I see the old pods being terminated, and I see 3 new pods like freshly created and just like 10 seconds old. And if I look at the web UI, I see a big crash, and it's going to take some time to recover. Why? Because first, I had like these workers making requests like continuously, and at some point, I had no backends at all. So what's going on right now is that the requests to RNG are going to time out. But it's going to take a while, because when I don't have any available backend, instead of immediately telling like connection refuse or no route to destination or etc., it's just going to time out, as if like I was trying to reach an IP address like that doesn't exist. Yeah, and if we give it a few minutes, it's going to come back up. And if I feel really impatient, I could like give a kick into the worker pods by doing like kubectl delete pods with the label app equal worker, and that would recreate the worker pods immediately. And so very quickly I should see the load coming back up. Yeah. Right. How do we scale the nodes themselves? So this will be strongly dependent on how we set up the cluster. If we're using a managed Kubernetes cluster, very often there will be direct API calls to do that. Like for instance, if we are on Google Cloud, it will be something like with the CLI, like gcloud container cluster -- scale, and that's going to automatically add nodes to the cluster. And within a few minutes, when I do my kubectl get nodes, boom, I see nodes up and running. If I'm managing my cluster myself, it depends on how I deployed my cluster. Here, for instance, what we did is that we created a bunch of Ubuntu instances, like using the basic Ubuntu LTS image, like nothing fancy. These are running on EC2, and I'm just using like the default Ubuntu image. And when I want to add a node, I install a container engine, in that case Docker. I install the Kubernetes packages, and then specifically because I deployed this cluster with kubeadm, which is one of the many ways to install them, I have a command that I can run to say basically kubeadm join this node with this secret token and join this control plane. And then the node is going to connect to the control plane, retrieve like certificates, like the kind of basic, the basic marbles to get started. And then it's going to use the secret token that I passed to authenticate itself with that cluster, and then dynamically join the cluster. But this is specific to when you use kubeadm. There are many other ways to do that. Given the questions that you ask, I guess that you might think, okay, I'm going to have to run Kubernetes clusters, and I need to learn not only about how to use them, but also how to operate them. If you're interested, if you look on container.training, there is a deck about how to operate and like basically Kubernetes for ops and admins, which deals with these things more in depth. Yeah. Other questions? Okay, so there are 2 more things that I would like to cover today, which are labels and selector and rolling updates. I'm going to be mindful of time, so I'm going to take some shortcuts compared to what's in the slides. So for labels and selectors, we started to touch that a little bit when I explained, okay, how how is it possible that we are sending traffic to these pods of the daemon set? Because of the labels and because the service is defined as send traffic to all the pods that have this specific label. So this means that we can use labels to configure load balancing. How do we do that? So here, for instance, I would like to remove a pod from the load balancer. So currently, let me see like this. Here on top, that's the logs for all the RNG pods. And maybe you can see on the left, there is a red pod, a dark blue pod, and a light blue pod. I would like to remove the red pod from the rotation. So if I freeze frame for a second to get the name of that pod, it's RNG ASCII 88F. Okay. So I would like to remove that pod from rotation. So I could remove the label, like the label app equal RNG. But if I do that, what's going to happen is that the daemon set is going to recreate a replacement pod immediately. Because if we look at the definition of the daemon set and how it works, the job of the daemon set is to make sure that we have one pod matching this per node. And matching this includes with label app equal RNG. So if I touch to this RNG label, automatically another replacement pod will be created. Okay, so if I want to fiddle with the load balancing, I need to add another label, and I need to use that label. Okay, so we're going to do that. I'm going to do kubectl. Okay, let me do that in that screen because it will be bigger. So I'm going to use another label called enabled, and with value yes for the pods that should be receiving traffic. So first, I'm going to add that label to all my pods. So kubectl label pods enabled equal yes. And I want to put that on all the pods that have app equal RNG. Okay, done. Now I will edit the service definition so that it uses this label. So there are many ways to edit an object, but one that is quite convenient is kubectl edit. So kubectl edit service RNG. This is going to download the YAML file, open it in an editor, then I can make changes, save, exit, and when I exit, it's going to send back the modified file to the API server. So that's the definition.
So we don't need to restart the services?
Sorry?
So we don't need to restart the services to make that?
Do we need to list the services?
No. Restart.
List, sorry.
Restart.
Oh, do we need to restart the service? No, this will be entirely dynamic. That's the whole point, yeah. So with Kubernetes, I can't really restart a service because there is no process associated with the service. The service, that's why I said earlier, like I liked the previous name before, a portal, because a portal is like, okay, this is this door that takes me to something else. A service in Kubernetes is a network construct, and there is no associated process to it. It's just in this cluster, it's a bunch of IP tables rules, but in other clusters, it might be something else. So here, I'm going to go to the selector here, and I'm going to add a second rule in the selector, enabled, colon, yes. Here, to save us some time and frustration, we have to use a string. If I just put enable yes like that, we're going to get a super weird error message because in YAML, yes becomes true, like the Boolean value, and a Boolean value can't be a label. So that's a little gotcha in YAML and Kubernetes. So I have to put enabled yes, like with quotes to say, yeah, this is really a string, not a Boolean value. I do that. So this is kind of pushing back the updated service definition. No change because the set of pods is still the same. I changed the query, if you will, but the result of the query is the same, so that didn't affect anything. But now I can touch this enabled label, I can change it to add and remove services. So for instance, remember I said I want to remove the red service. So I do kubectl label pod. So that's this one, RNG SKey88F, and I want to remove the enabled label. So to remove a label, the syntax is a little bit different. You put the name of the label and then you put minus. That means drop that label. I do that and immediately, you see on top, I'm sorry if you can see colors, but the red pod is not visible anymore. It stops showing up above. And if I look in the web UI, the performance is now going to drop to 20 per second. It's not going to be visible immediately, but and I can repeat that operation. I can say, okay, now drop the label from RNG GZ9 and 5. So that's the light blue pod. Oops, sorry, GZ9 and 5. So that's the light blue pod. So here we're going to only keep the dark blue pod. That's it. So that's great because it means that without knowing exactly how the load balancing works under the hood, without having to worry about kube proxy, IP tables, whatever, I am able to add and remove backends to a load balancer. It takes effect instantly, and I can manipulate my load balancer configuration live without requiring root access to load balancer, without requiring me to open a ticket with the networking team, etc., 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 etc. Okay, so that's what we did. So this can be used for debugging. Like if I need to remove something from the load balancer, I remove the label, do some tests. Yeah. Is there a? I'm sorry, I can't hear you. I'm very sorry, but I really can't hear you from the back of the room.
Is there a way in which the state information of the load balancer is captured?
Oh, is there a way to capture the state information of the load balancer? You mean state, like to make sure that a given client always will go to the same backend, or? Like to see the backends, or? So if I do kubectl describe, on describe service RNG, I see the list of endpoints, and that tells me where the traffic is going. Oh, is there a push notification? Like, okay, like for instance, I want to know when a service is, okay, I see what you mean. Right, that's an excellent question, and yes, we can do that. For instance, I can do, okay, I want to be aware when something changes in my load balancer. So I'm going to split this again, and I'm going to do kubectl get service RNG -w, the same watch option that we used for pods earlier. And then I'm going to change something. So for instance, I'm going to re-add a label to a pod. So kubectl label pod RNG something like SK, etc. Enabled equal yes. So when I do that, I will see that pod reappear up there. And here I will see an update as well. Oh, no. Okay, maybe that's not the right object that I need to monitor. I think it's the endpoints object that I need to monitor. Let's try again. Okay, so rewind. Let's pretend nothing happened, and let's try again with the endpoint object. So I'm going to, yes, that's it. Yeah, that's what I did. I did kubectl get endpoints RNG -w, and now I'm streaming the endpoints. So if I want to be aware each time something changes, I can do it that way. Oh, if could I stream it to something else? Yeah. So in that case, I'm just streaming with the CLI, so it's just re-showing the object. But on the API level, I can do the equivalent of a watch, and then I get the updated object, and I can. Okay, so I think the plug on which I had connected my laptop was actually not connected to power, and so my laptop just lost power. So let's see. Okay. Now I have power. I'm going to report that really quick. Huh? Do we have, sorry? Yeah, I know. I just wanted to. So we've seen selectors and labels. The last chapter was about rollouts, and I'm just going to give you the high-level picture. When we want to push a new version of a service, we do that by changing. Yeah. I'm just going to let me just restart my graphic environment, and then let's see, Juke. There we go. And then slides. And then this goes here. And then we were around here. So when we do a rolling update, so we want to update one of the services, we do that by changing the deployment object. And I alluded to that earlier today. When we change the deployment object, it's going to create a new replica set, and then it's going to scale up that replica set and scale down the old replica set. And there are a few parameters that we can set here to say how many new pods we want to create and how many old pods we want to remove. Just to show you in concrete terms what this looks like, I'm going to reconnect to my cluster, reattach to tmux. And so, for instance, if I want to upgrade the container image used by worker, I can do kubectl set image deployment worker, I think. Just making sure. Yeah. Worker equal dockercoin/worker :v 0.2. So that means set image it's a helper. It's going to get the YAML of the deployment, patch it, like change something in it, and then push it back. So that means get the deployment worker and change the image for the container worker inside that deployment and set it to this image. So we do that, and that's all we have to do, and then it's going to proceed with the rolling updates. Okay, you can try that like this afternoon if you want. I just would like to give you like the conclusion quickly. So how do we get started to containerize applications? So very often what I tell to people who get started with Kubernetes is first make sure that you got the basics. So make sure that you are already using containers in dev. Because if you're not using containers in dev and you want to jump directly to using Kubernetes, you're going to have a bad time. So make sure that you're using containers. It could be with Docker files and Compose files, just like I showed this morning. It could be something else. I think that Compose is a really great development tool because remember what we did this morning. We cloned the repo, we did Compose up, and a couple of minutes later, we had the app up and running. Fun fact, that app was written almost 4 years ago, and the code hasn't changed by a single line since then. So code that has been written for Docker demos 4 years ago still works today with Kubernetes. The images that we've built 4 years ago still work today with Kubernetes. So that's pretty nice. And once you have containers in dev, then you can start thinking about CI, maybe doing some CD to staging, like have a specific branch going to staging. And that does not require clusters and orchestration. You can do that on single nodes. And then after that, you can start thinking about orchestration and things like Kubernetes. start with a managed Kubernetes cluster. You might end up having to run it yourself, but start with a managed cluster because you will save yourself a lot of problems and extra hassle. Prefer multiple small clusters rather than one big cluster, because if there is a problem, you will have one small problem instead of a big one. Namespaces, we mentioned them earlier this morning, so I can skip that. I have a few links here to chapters about namespaces, network policies, and role-based access control. Stateful services are if you want to run databases, message queues, and things like that. You don't have to. Very often, people ask me, hey, should I run my database on Kubernetes? Then I tell them no. But if they ask me, should I run my databases, like plural, on Kubernetes? And I say, maybe. What I mean by that is that running a stateful service on Kubernetes is a lot of extra work, especially if you're getting started with Kubernetes. So there is no shame in keeping your databases outside. Now, if you are running lots of databases, like tens, hundreds, thousands, it might be a good idea to leverage Kubernetes because you will leverage the automation and all the features we saw for pods that repair themselves, etc., for databases as well. There is another thing that if we had more time, I wish I could have shown you, which is ingresses, which lets us handle HTTP traffic in special ways. Loggings and metrics, I alluded to that earlier today. Configuration of applications, same thing. I have links here to a section showing how to inject environment variables and how to use configuration maps to manage application configuration. And for stack deployment, today we've used mostly kubectl and we created resources almost manually. The next step to that is to get the YAML, clean it up a little bit because the YAML has lots of information, but you can drop a lot of that information and kind of boil it down to the essential, and then you can version that YAML in your repo and use that to deploy. So instead of telling someone, oh, you need to kubectl create this, kubectl run that, kubectl expose, you just give them a nice little heap of YAML and they just create that YAML and that's it. And then you have other tools like Customize and Helm that will let you template that YAML so that it can be customized and tailored for specific scenarios, so that you have one core YAML and you specialize it for dev, for pre-prod, for prod, etc., etc. Last step, I've put it last because I want to make sure that you remember about that. When you start learning about Kubernetes, very quickly, you will be ahead of the rest of your team in terms of what you know about Kubernetes. And there are many concepts that are new and sometimes weird or bizarre, and mind the gap. Remember that now you know more about containers and Kubernetes than the rest of your team, and that once you start talking about pods and services and selectors and etc., a lot of people are going to give you a blank stare if you don't take the time to spread that knowledge as well. I've put a few questions here. It's a kind of good litmus test. Do I have good answers to these questions when I start implementing containers and Kubernetes in my team? If I do have good answers to that, great. If I don't, maybe I should start there to make sure that I won't end up with a small team of Kubernetes experts and everybody else kind of like, how do we grasp that thing? That's it. I have a bunch of extra links and resources. Most importantly, the PyCon organizer would like me to tell you that you should rate this workshop using that link that I will keep on the screen. If you want to know and learn more about Kubernetes, if you go on container.training, you will find slides decks that I used for 1 day, 2 day, even longer workshops. And that's it. And the last words as a shameless self-promotion. I also do that as a professional trainer, so if you liked this and you want more of it, talk to me. I'll be happy to come and train your team. Thank you, and I'll be here to answer questions and during the whole conference as well.